Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to begin with a place that seems so simple, it almost feels like there should be nothing to say about it at all. The vacuum, empty space, the quiet gap between things, the stretch between one dust mote and another, the darkness between the stars, the pause inside a glass jar after the air has been pumped away. It sounds like the easiest thing in the world to describe. A vacuum is what you get when everything has been removed. No air, no dust, no sound, no drifting crumbs from a late-night biscuit, just nothing. But in physics, nothing has a habit of becoming very interesting the moment you look closely at it. So tonight we're asking a question that begins gently enough and then opens into some of the deepest ideas in modern science. What is the vacuum really made of? Is it truly empty, like a perfectly cleared room after everyone has gone home, or is it more like a stage where the actors are invisible but the performance is still happening? When scientists speak of empty space, do they mean an absence, or do they mean something that is present in a quieter and stranger way than ordinary matter? And while we are here together, settled into this small pocket of time, I would love to know where you're listening from tonight. Are you in a city where the lights blur the stars, or somewhere quiet where the night sky looks wide and dark? And if you happen to glance around your room, what does emptiness feel like to you? Is it the space above your bed, the air between your hands, the silence after the day has finally stopped asking things of you? If you find this little journey soothing, or if science helps your mind settle down after a long day, I would be very grateful if you liked the video and subscribed. It helps this calm corner of physics reach other sleepy travellers who might enjoy learning something strange while their thoughts begin to loosen. And I do hope tonight's subject does not keep you awake too much. The vacuum can be surprisingly lively, which is not always what one wants to hear at bedtime. But we will approach it slowly without hurry, one quiet idea at a time. No need to solve the universe tonight. We can simply wander through it, noticing that even what looks empty may be more crowded with meaning than it first appears. When most of us hear the word vacuum, we probably think of a place with no air. Maybe a sealed chamber in a laboratory, maybe outer space, maybe the inside of a vacuum flask keeping soup warm with impressive dedication. In everyday language, this is perfectly reasonable. A vacuum is a region where matter has been removed, especially gas. If you take a container and pump out the air, you create something we would call a vacuum. There may still be a few atoms drifting around because nature is very difficult to tidy completely. But compared with the thick soup of molecules we breathe every day, the chamber is mostly empty. It is empty enough that sound cannot travel well, flames cannot burn normally, and a feather and a coin would fall together if gravity were allowed to do the rest. This everyday vacuum already feels dramatic because we are creatures of atmosphere. We live pressed beneath a blanket of air. Though we rarely notice it, every breath depends on it. Every sound reaches us because of it. Even the simple act of boiling water depends on pressure from the surrounding air. Remove that air, and familiar things start behaving strangely. Water can boil at lower temperatures. Sound fades because there are not enough particles to carry vibrations. Objects do not slow down from air resistance in the usual way. The vacuum, even in this simple sense, is not just empty. It is a place where the usual support system of everyday life has been taken away. That is already enough to make it interesting. But physics does not stop there, because physicists have a long history of taking a simple word and asking whether it is secretly hiding an entire universe behind it. In classical physics, especially in the older view of nature, empty space was often treated as a passive background. Matter moved through it, light crossed it, forces reached across it. Space was the container, and the objects were the important things inside. If there was nothing in the container, then there was simply nothing happening. This idea is comfortable, because it matches how we think about rooms and boxes. Take the furniture out of a room, and the room is empty. Take the apples out of a basket and the basket has no apples. Take the air out of a jar and the jar has a vacuum. But the universe is not quite a room. An empty space is not quite an empty basket. The more carefully scientists studied light, matter, atoms, energy and gravity, the harder it became to treat space as a silent container. Something about the vacuum kept showing up in the details. It appeared in the way light travels. It appeared in the behaviour of atoms. It appeared in the forces between tiny objects. It appeared in questions about why particles have mass, why the universe expands, and why the very idea of nothing may not survive contact with quantum physics. There is a useful first distinction here, and it is worth making slowly. A vacuum in the everyday laboratory sense means a region with very little matter. It means there are few particles such as atoms or molecules moving around. A vacuum in the deeper physical sense means the lowest energy condition of space itself. That sounds like a small change, but it is enormous. The first kind of vacuum asks whether we have removed the stuff from a region. The second asks what remains when space is in its quietest possible state, and modern physics suggests that even the quietest possible state is not simple emptiness. Imagine turning off every appliance in a house at night. The lights are off, the television is off, the kettle is cooled, no one is walking around. It feels quiet. But if you listen closely, there may still be a faint hum from the walls, a soft settling of pipes, the distant movement of air, the tiny clicks of cooling metal. The house is not active in the obvious daytime sense, but it is not an absolute absence of activity either. The vacuum in modern physics is a little like that, though much stranger. It is not full of ordinary particles in the way air is full of molecules, but it is not a dead silence. It has structure, it has properties, it can influence things, it can respond. One reason this is so surprising is that our senses are not built to detect the vacuum directly. We notice objects. We notice warmth, light, pressure, sound, texture. We notice the table because our hand stops there. We notice air when it moves as wind or when it is missing from our lungs. But empty space does not bump into us in the ordinary way. It seems like the absence of experience. So our intuition says that if there is no matter there, then there is no thing there. Yet scientific instruments and mathematical theories have taught us again and again that intuition is not always a reliable guide at scales too large, too small, too fast, or too quiet for daily life. The vacuum of outer space is a good example. We often call space empty, and compared with Earth's atmosphere it certainly is. The air around you contains a huge number of molecules in even a small breath. Interplanetary space has far fewer particles. Interstellar space is emptier still by ordinary standards, though it is not perfectly empty. There are atoms, ions, dust grains, radiation, magnetic fields, cosmic rays, and the faint afterglow of the early universe passing through. Even the space between galaxies, which seems almost unbearably empty, is not pure nothing. It contains thin gas, light, fields, and the influence of gravity stretching across vast distances. Space is sparse, not blank. Still, even if we could remove every atom, every dust grain, every photon of light, every wandering bit of ordinary radiation, modern physics would not let us say that absolutely nothing remains. This is where the story begins to move from vacuum as airlessness to vacuum as a physical state. In quantum field theory, the world is not made primarily of little solid objects sitting inside empty space. Instead, every type of particle is understood as an excitation of a field that exists throughout space. Electrons are connected with an electron field. Photons are connected with an electromagnetic field. Other particles have their own fields. These fields are not like fields of wheat in a countryside, though that would be much easier to picture and much more relaxing to harvest. They are physical systems spread everywhere, and what we call particles are disturbances or packets of energy in them. Now here is the important bedtime-friendly version. If fields fill all of space, then empty space is not the absence of fields. empty space is what the fields are doing when they are in their lowest energy condition. The vacuum is not a stage with no stage. It is more like the stage with no visible performers, but the floor, lights, wiring and hidden machinery are still there. A particle appears when a field is excited, a little like a ripple appearing on water. But even calm water is still water. In a similar way, a field with no particles present is still a field. It has a quiet condition, and that quiet condition is what physics calls the vacuum. This is one of the places where language becomes tricky. The word empty is useful, but it can mislead us. Empty of what? Empty of air, empty of atoms, empty of light, empty of particles, empty of fields, empty of energy. The answer changes depending on which level of physics we are discussing. A jar can be empty of soup but full of air. A room can be empty of furniture but full of light. Space can be empty of atoms but full of fields. And the quantum vacuum can be empty of particles while still having activity that shows up in experiments. This does not mean that empty space is secretly packed with tiny solid objects popping around like popcorn. That image is common, and it can be fun, but it is also easy to take too literally. The vacuum is not a little storm of ordinary particles appearing in the same way birds appear in a garden. The deeper truth is more subtle. Quantum fields cannot be made perfectly still in the old classical sense. Their lowest energy state still has fluctuations, limits, and measurable consequences. The vacuum is quiet but not frozen. It is not full in the ordinary way, but it is not nothing. One of the gentlest ways to approach this is through the idea of a perfectly still object. In everyday life, we can imagine something at rest, a book on a table, a cup by the bed, a sleepy cat who has decided that movement is unnecessary for the next several hours. But in quantum physics, when we look at very small systems, there are limits to how precisely certain features can be settled at once. Nature does not allow every quantity to be sharpened into perfect certainty. That means even the lowest energy condition of a field is not a completely motionless, featureless blank. There is a kind of irreducible restlessness built into the rules. This restlessness is not noise in the ordinary sense. It is not caused by poor instruments or tiny bits of dust we forgot to remove. It is part of the description of nature at its most basic level. When scientists calculate the behavior of atoms, particles and fields, the vacuum state matters. It affects what particles can do, how forces behave, and how tiny systems shift their energy. In some cases, the vacuum can even produce measurable forces between objects placed very close together. That is not the behavior of nothing. Nothing does not usually lean on things. This is why the question of what the vacuum is made of becomes so strange. In ordinary language made of suggest ingredients, a cake is made of flour, sugar, butter and eggs. Unless one has been adventurous and created something that future guests will discuss politely, but never request again. A chair is made of wood or metal. Air is made of molecules. But the vacuum is not made of ingredients in the everyday sense. It is not a substance sitting inside space. It is the baseline condition of the fields that define what can happen in space. It is less like a material and more like a state of the underlying systems of nature. That sounds abstract, but we can keep it grounded. The vacuum has properties. It can be influenced by boundaries. It can be affected by fields. It can help determine the masses of particles. It may contribute to the expansion of the universe. It is involved in some of the biggest unanswered questions in physics. So even if we cannot scoop up a jar of pure vacuum and pour it into a bowl, we can still say that the vacuum is physically meaningful. It is part of the machinery of reality. Historically, this has been a long and winding change in human thought. Ancient philosophers argued about whether empty space could exist at all. Some thought nature would never allow a true void. Others believed that atoms needed empty space in order to move. Much later, experiments with pumps and barometers show that air could be removed from containers and that pressure was a real physical thing, not just an invisible habit of the world. The vacuum became something engineers could make, improve, and use. Then, With electromagnetic theory, relativity, and quantum physics, the idea deepened again. Empty space became connected with light, fields, energy, and geometry. Each century took the vacuum and made it less empty than before. There is something quietly funny about that. Humans spent ages trying to create nothing, only to discover that nothing was extremely hard to get and perhaps impossible in the absolute sense. We pumped out air and found leftover gases. We improved the pumps and found radiation. We cooled systems down and found quantum motion. We removed particles and found fields. The more carefully we cleaned the room, the more we discovered that the room itself had opinions. This does not make everyday emptiness false. The space inside a vacuum chamber really is emptier than the air around us. Outer space really is more empty than a room. A region with no particles is genuinely different from a region full of gas. But physics often works by showing that ordinary ideas are useful in one setting and incomplete in another. The vacuum is empty enough for many purposes, but not empty in the deepest way. It is a calm surface that becomes more complicated when seen with the right instruments and theories. A good comparison is silence. If you sit quietly at night, you may say the room is silent. That is true in the ordinary sense. There is no conversation, no music, no traffic close by. But a sensitive microphone might detect faint vibrations. Your ears might notice your own breathing, the pulse in your body, the soft creak of the building. And even if all sound waves were removed, the physical possibility of sound would remain because the room has air and surfaces and pressure. Silence is not always an absolute thing. It depends on what you're listening for. The vacuum is similar. It may be empty compared with air, but when physics listens closely, there is still something to describe. The deeper we go, the more we see that the vacuum is tied to the question of what reality is when nothing obvious is happening. A particle moving through space is easy to imagine. A planet orbiting a star is easy enough. A beam of light crossing a room feels familiar, even if light itself is wonderfully strange. But the vacuum asks us to consider the background condition that allows all of those things. It asks what remains before the actors enter, before the light is switched on, before matter gathers into atoms, stars, planets, and people, sitting quietly with a video playing in the dark. And this question is not only philosophical, it matters for technology and cosmology. Vacuum physics is important in particle accelerators, where beams of particles need clear paths. It matters in electronics, materials science, lasers, and precision measurements. It matters in astronomy because the vacuum of space is where light travels across billions of years. It matters in cosmology because the energy of the vacuum may be connected to the accelerated expansion of the universe. It matters in particle physics because the vacuum is shaped by fields such as the Higgs field, whose presence changes how particles behave. The vacuum is not a blank page outside the story. It is part of the story's grammar. This is where our journey tonight begins, not with the most difficult mathematics, and not with the sharpest edge of theory, but with a change in expectation. We're going to take the word nothing and handle it carefully. We are going to separate airless space from empty space, and empty space from the quantum vacuum. We are going to see why the vacuum can fluctuate, why it can produce measurable effects, why fields matter more than little balls moving through a void, and why the emptiest parts of the universe may still carry energy that shapes the fate of everything. For now, the most important idea is simple enough to take with you as your thoughts settle. The vacuum is not what remains when reality has been removed. It is part of reality. It is the quietest condition of the fields that fill space. It is what is there when ordinary matter is gone, when the air has thinned away, when no visible object occupies the room. It is not crowded like a city or thick like fog. It is not a hidden gas or a secret dust. It is a physical state, calm but not featureless, empty but not meaningless. So as you rest there wherever you are, notice the space around you for a moment. The gap between your hands and the blanket, the room between the ceiling and the floor, the dark stretch outside the window. It all seems obvious, open, available, almost too ordinary to deserve attention. But the universe often hides its deepest ideas in the places we stop noticing. The vacuum is one of those places. It is the quiet room where nothing turns out to have structure, where emptiness becomes a scientific object, and where the absence of matter begins to reveal the presence of fields. And before we can understand the restless quantum vacuum, before virtual particles and strange forces and cosmic expansion enter the scene, we need to clear away the first misunderstanding, because the vacuum of a laboratory, the vacuum of outer space, and the vacuum of fundamental physics are related, but they are not the same thing, and that difference is where the next part of the story begins. Now that we have stepped into the quiet room where nothing is not quite nothing, it helps to slow down and ask what people usually mean when they say empty space. Because the word empty seems simple until you try to use it carefully. A cup can be empty because there is no tea in it, while still being full of air. A room can be empty because no one is standing in it, while still holding furniture, dust, light, warmth, and the faint smell of whatever was cooked earlier. A pocket can be empty of coins and still contain a receipt, lint, and one mysterious crumb that seems to have survived several laundry cycles. Emptiness depends on what you expected to find there. In physics, that small detail matters very much. When we say empty space in ordinary conversation, we often mean a space with nothing solid in it. The gap between you and the wall is empty because you can move your hand through it. The space above a table is empty because no book or cup is occupying it. The room after people leave is empty because the people are gone. But from a physical point of view, that room is still very busy. It is filled with air molecules flying in every direction, bouncing off walls, slipping into your lungs, carrying sound, holding moisture, and pressing on every surface with a force so familiar that we almost never notice it. The room is not empty in the sense of being free from matter. It is only empty in the sense that it is free from the things we are paying attention to. This is the first great misunderstanding about vacuum. We often imagine that a vacuum is simply empty space, but most of the time what we really mean is airless space. A vacuum cleaner, despite its proud name, does not create a perfect nothing inside your living room. It makes a region of lower air pressure, and the surrounding air rushes in carrying dust with it. It does not suck in the magical sense. It creates a pressure difference, and the atmosphere does the pushing. So the next time a vacuum cleaner groans across the carpet as though it is heroically inhaling the crumbs of civilization, you can remember that the real worker is the air around it, shoving everything toward the lower pressure region. The machine gets the credit, but the atmosphere is doing a surprising amount of the labour. The same idea applies to many devices that use vacuum in daily life. A suction cup sticks to a wall, not because the cup has developed affection for the tile, but because air has been pushed out from underneath it. The air outside presses it into place. A drinking straw works because you lower the pressure inside your mouth, and the atmosphere pushes liquid upward. Even sealed food packaging often uses reduced air pressure to slow spoilage and protect contents. In each case, vacuum means less gas than usual, not absolute nothing. It is a practical condition, not a philosophical disappearance act. Air pressure is so ordinary that it becomes invisible to thought. We live at the bottom of an ocean of gas, and every moment that ocean presses on us. The only reason we are not crushed flat like a very unfortunate pancake is that our bodies push back from the inside. The fluids and gases within us balance the pressure outside. When the pressure changes, we notice it in our ears on a plane, or in the feeling of a storm arriving. But most of the time, atmosphere is simply the background support of life. It carries scent, weather, warmth, and breath. It makes birds possible, clouds possible, conversation possible. Remove it, and the familiar world becomes hostile very quickly. A laboratory vacuum begins with removing that atmospheric gas. Scientists use pumps to pull molecules out of a chamber, lowering the pressure inside. At first, this sounds straightforward. You put the chamber under a pump, turn the machine on, and the air leaves. But nature does not give up its molecules easily. gas clings to surfaces. Tiny amounts of water vapour hide on metal walls. Materials slowly release trapped molecules in a process called outgassing. Seals leak, even if only slightly. Dust remains unless everything is cleaned with great care. The deeper the vacuum you want, the more the project becomes less like emptying a bucket and more like trying to make an old house completely free of dust forever. You may improve it beautifully, but the universe keeps finding little corners. This is why scientists speak of different grades of vacuum. A rough vacuum has removed a great deal of air compared with normal conditions, but still contains many gas molecules. A high vacuum contains far fewer. An ultra-high vacuum is cleaner still, used in sensitive experiments, where even a few stray atoms can interfere. These distinctions matter because a vacuum is not all or nothing. It is a measure of how much has been removed and how little remains. Even the best laboratory vacuum is not perfect emptiness. It is an extraordinary achievement of engineering, but it is still a thin population of molecules wandering through a chamber that has been scrubbed, sealed, baked, pumped, and watched with more patience than most of us can bring to assembling flat-pack furniture. To appreciate how dramatic this is, imagine the air around you as an immense crowd of tiny particles. They move so quickly and are so numerous that they create what feels like a continuous substance. When wind touches your face, you do not feel individual molecules politely introducing themselves one by one. You feel a smooth flow because there are so many of them. A vacuum chamber removes most of that crowd. The remaining particles are fewer, with more space between them, and they may travel farther before colliding with anything. The lower the pressure, the lonelier each molecule becomes. It is not that space itself has changed. The contents have thinned. Outer space is often treated as the ultimate vacuum, and in many practical ways it is. Compared with Earth's atmosphere, it is astonishingly empty. Above the atmosphere, there are too few gas molecules to breathe, too few to carry sound as we know it, too few to give wings the ordinary lift they need. This is why explosions in space do not boom through the void the way they do in cinema, unless the filmmakers have kindly included sound for our emotional convenience. Sound needs a material medium, such as air or water or metal, to carry its vibrations. In the near emptiness of space, there is no thick atmosphere to pass those vibrations along to your ears. Space can be visually dramatic, but acoustically it is a very poor conversationalist. Yet even outer space is not truly empty. Around Earth, there are particles from the solar wind, bits of plasma, traces of the upper atmosphere, radiation, micrometeoroids, magnetic fields, and satellites that occasionally make engineers nervous. Between planets, space contains charged particles streaming from the sun, dust grains, magnetic fields, and light. Between stars, space becomes thinner, but it still contains gas, dust, cosmic rays, and radiation. Between galaxies, it is thinner again, but not a perfect absence. Even in the broadest cosmic voids, where galaxies are scarce and distances become almost impossible to imagine, there is still not absolute nothing. There are fields, faint particles, ancient light, and the stretching fabric of space-time itself. This matters because the popular image of space as a vast black nothing can mislead us. Space is dark because there is very little matter to scatter light into our eyes, not because it contains no light at all. Space is silent because there is not enough gas to carry ordinary sound, not because nothing ever happens there. Space is cold in one sense because an object in shadow can lose heat by radiation and receive little back. But it is not cold in the same way a freezer is cold, because temperature usually describes the motion of particles, and in a near vacuum there are not many particles to share warmth with your skin. The vacuum of space is not a freezer, not a silent room, and not a perfect blank. It is a sparse environment where our Earth-shaped instincts do not always apply. This is one reason astronauts wear pressure suits. It is not only about oxygen, though oxygen is certainly important if one wishes to continue with the afternoon. The suit also maintains pressure around the body. Without sufficient pressure, Bodily fluids are not held in their usual state, gases expand, and the body enters severe danger. Space does not pull a person apart like a dramatic villain. It simply fails to provide the pressure and breathable atmosphere that our bodies evolved to expect. Again, the vacuum is not an active monster. It is an absence of support. Sometimes the most dangerous thing is not what attacks you, but what quietly stops being there. The same confusion appears when people talk about nothingness. We use nothing in many everyday ways. There is nothing in the fridge, we say, while ignoring a jar of mustard, half an onion, and a container whose contents are now a matter for archaeology. There is nothing on television, meaning nothing we want to watch. There is nothing in the room, meaning nothing important to us. Human language is practical. It does not aim for perfect physical precision while someone is looking for a snack. But physics asks for clarity. Empty of air is different from empty of matter. Empty of matter is different from empty of radiation. Empty of particles is different from empty of fields. And empty of fields may not be a meaningful condition in the theories that describe our universe. The great misunderstanding, then, is thinking that all these emptinesses are the same. They are not. An airless chamber is not the same as a region free of all particles. A region free of ordinary particles is not the same as the quantum vacuum. Outer space is not the same as metaphysical nothingness. A vacuum is not a hole cut out of reality. It is a physical situation inside reality, and it always has to be described with respect to what has been removed and what remains. This distinction became clearer over centuries. Early thinkers disagreed about whether a true void could exist. Some argued that empty space was impossible, because nature would rush to fill it. Others believed that empty space was necessary, because without gaps, atoms could not move. For a long time, these arguments were philosophical, because no one could easily make a strong vacuum and study it. Then experiments with air pressure changed the discussion. When scientists learned how to pump air from vessels and measure pressure, the vacuum became something practical and testable. It moved from an idea debated in words to a condition created by machines. One of the classic lessons came from the barometer. A tube filled with mercury and turned upside down in a dish leaves a space at the top where very little matter remains. The height of the mercury is supported by atmospheric pressure pushing on the dish. This showed that air has weight and pressure, and that a space with very little air could exist. It also helped reveal that the atmosphere is not an endless, weightless presence, but a physical layer surrounding Earth. The vacuum was no longer just an argument. It was sitting there in glass, quietly proving a point. Later, air pumps allowed scientists to do more dramatic demonstrations. They could show that a bell ringing inside a vacuum chamber becomes harder to hear as the air is removed. They could show that animals need air to survive, that flames need oxygen to burn, and that pressure differences can be powerful. These experiments helped separate the idea of emptiness from the idea of invisibility. Air is invisible most of the time, but it is not nothing. Remove it, and the effects are immediate. The vacuum taught humanity that something unseen can still be deeply physical. This lesson is still important. Many of the most significant things in physics are not directly visible. Air, magnetic fields, radio waves, radiation, gravity, and quantum fields all reveal themselves through effects. We know them by what they do. The vacuum fits into that tradition. You cannot see a vacuum in a jar as though it had a colour. You know it is there because of pressure gauges, the behaviour of objects inside it, the absence of sound transmission, the way particles travel, and the performance of instruments. It is defined by conditions, not appearance. But there is a second layer to the misunderstanding. Once people accept that an airless region can exist, they may imagine that science has finally reached true nothing. Remove the air, remove the dust, remove the atoms, and surely at the bottom there is a clean blank. Yet modern physics says that this clean blank is not the end of the story. When ordinary matter is removed, the fields of nature remain. The electromagnetic field does not vanish just because a chamber contains no air. The fields associated with particles do not disappear from space simply because no particles are currently being detected there. Gravity still gives structure to the region. Space-time itself still has geometry. The vacuum, at the deepest level, is not the same as a perfectly empty box. It is the lowest energy state of the fields. This phrase, lowest energy state, can sound a little technical, but the idea can be approached gently. Think of a pond after the wind has stopped. There may be no large waves. No splashing ducks, no thrown stones, no little boat making ripples. The pond is calm. But calm does not mean the water has ceased to exist. It means the water is in a quiet condition. Now imagine that the fields of physics are something like that, though not made of water and not sitting in space in the ordinary way. Particles are like disturbances in the fields. Remove the disturbances, and you have not removed the fields. You have found their quietest condition. That quiet condition is what physics calls the vacuum. This is why saying the vacuum is made of fields is both useful and slightly delicate. The vacuum is not a substance like fog, nor is it a fluid sloshing between planets. It is not a hidden material waiting to be bottled. Rather, it is the baseline state of the fields that are part of our best description of nature. If those fields can be excited, particles may appear. If they are not excited, we call the state empty of particles. But it's not empty of the possibility of particles, nor empty of the rules and structures that govern them. The vacuum is not the absence of the game. It is more like the board when no pieces are currently moving. Except in quantum physics, even that board has a strange kind of restlessness. At this point, it's easy to overcorrect and imagine the vacuum as crowded in a familiar way, as if empty space were secretly full of tiny marbles popping in and out. That image is often used because it is simple and memorable, but it can cause trouble. The quantum vacuum is not full of ordinary particles that just happen to be shy. When physicists talk about fluctuations, they are describing the behavior of quantum fields in their lowest energy condition. It is a real and measurable feature of the theory, but it is not the same as a swarm of little objects flickering like fireflies. The truth is subtler, and subtler things do not always make good cartoons, which is a pity because physics could use more calming cartoons. Still, measurable effects are the anchor. The vacuum can influence atoms. It can affect forces between closely spaced surfaces. It matters in the behavior of particles. It plays a role in high-precision experiments. It may even connect to the expansion of the universe. If the vacuum were merely a word for nothing at all, it would not show up in these ways. Nothing has no properties. Nothing cannot be polarized, strained, structured, or measured. The physical vacuum can be. That is why scientists treat it not as an empty mistake, but as a subject. A helpful way to keep the idea clear is to think in layers. The first layer is ordinary empty space around us, which is actually full of air. The second layer is a practical vacuum, where much of the air has been removed. The third layer is the vacuum of outer space, where matter is extremely thin but still present in small amounts. The fourth layer is an idealized region with no ordinary particles at all. The fifth layer is the quantum vacuum, the lowest energy state of the fields that fill space. The word vacuum may be used for several of these depending on context, and confusion begins when one meaning slips into another without warning. This is why someone might say space is a vacuum and be correct, while a physicist might add, with the gentle persistence of someone correcting a recipe, that it is not a perfect vacuum. Then another physicist might say, even a perfect particle-free vacuum is not nothing, because the fields remain. Then a cosmologist might wander in and mention dark energy, at which point everyone's tea has gone cold, and the vacuum has become the most crowded, empty subject imaginable. The important thing is not to feel lost in the layers, but to notice the pattern. Emptiness becomes more interesting the more precisely we define it. What seems like absence at one level becomes structure at another. The room with no people still has air. The chamber with little air still has stray molecules and radiation. Interstellar space still has gas, dust, light, and fields. The quantum vacuum still has field structure and fluctuations. Physics does not simply destroy the idea of emptiness, it refines it. It asks, empty relative to what? This also changes how we imagine the universe. Matter is not sitting inside a meaningless void. It is embedded in fields, shaped by space-time, bathed in radiation, and influenced by vacuum properties. The space between stars is not just the gap where nothing happens until you reach the next glowing object. It is the arena where light travels, where fields stretch, where particles stream, where gravity guides motion, and where the quiet baseline of reality continues. The vacuum is not scenery, it participates. For us living in air and warmth, this can feel remote. We do not experience vacuum directly. We experience pressure, breath, sound, and resistance. Our bodies are built for a world where space is filled with atmosphere, so it is natural that our intuition treats air as nothing and vacuum as extra nothing. But the more carefully we look, the more the simple picture softens. Air is something. Removing air creates a special condition. Removing matter leads to deeper questions, and at the base of those questions lies the idea that empty space is not the same as no reality at all. So when we ask what the vacuum is really made of, we must first let go of the most familiar answer. It is not just made of nothing because the word nothing is doing too much work. It is not just a lack of air because that is only the beginning. It is not just outer space because outer space contains more than our imagination often allows. The vacuum is a layered idea, moving from engineering to astronomy to quantum theory, and each layer reveals something different. The misunderstanding is not that people are foolish to call space empty. It is that ordinary language was never designed to hold all the meanings physics discovered. And now the path ahead becomes clearer. Once we understand that an airless space is not the same as absolute nothing, we can begin to ask what remains when even the last ordinary particles are removed from our picture. That question leads away from pumps, pressure, and chambers, and toward the deeper framework of modern physics, where fields are not optional decorations, but the basic ingredients of what we call particles, forces, and empty space itself. The vacuum is about to stop being a cleaned-out container and become something more like an invisible ocean, spread everywhere, usually calm, sometimes disturbed, and always present beneath the matter we can see. To understand why the vacuum is not simply a cleaned-out container, we need to step into one of the biggest changes in the way physics describes reality. It's a change that sounds strange at first, because it asks us to stop imagining the universe as a collection of tiny objects moving through empty space, like grains of dust drifting through a sunbeam. That picture is useful for many everyday purposes. It works well enough when we think about pebbles, planets, tennis balls, and the heroic crumb that escapes the plate and rolls under the sofa. But when we look deeply into matter, when we ask what electrons and light and the smallest known particles really are, the old picture begins to feel too stiff. Modern physics suggests that the universe is not built from little solid things sitting in a void. It is built from fields spread throughout space, and what we call particles are the visible disturbances of those fields. A field in physics is something that has a value or condition at every place. That may sound formal, but the idea is not entirely unfamiliar. Think of temperature in a room. Even if you cannot see temperature floating there like a mist, every point in the room can be warmer or cooler. A weather map shows wind or pressure spread across a region, and every place on the map has some condition associated with it. A magnetic field surrounds a magnet, and you can reveal its pattern with iron filings, as if the invisible has briefly agreed to draw itself for you. A field is not necessarily a solid object. It is a physical presence that can vary from place to place and can influence things. The electromagnetic field is perhaps the easiest example to begin with, because its effects are everywhere. Light is connected with the electromagnetic field. Radio waves, microwaves, visible colours, X-rays, and many other forms of radiation are all different ways this field can carry energy. When you warm your hands by a lamp, use a phone, see the glow of the moon, or receive a radio signal, you are dealing with the electromagnetic field. It is not a decorative idea placed on top of reality. It is part of how reality works. In older language, we might say light travels through space. In field language, we say light is a disturbance of the electromagnetic field moving through space. The difference may sound subtle, but it becomes important when we start talking about the vacuum. Quantum field theory goes further. It says that every kind of fundamental particle is associated with a field. There is an electron field, there are fields connected with quarks, there are fields associated with neutrinos, there are fields connected with the particles that carry forces. These fields are not little clouds surrounding individual particles. They are not painted around matter like halos. They exist everywhere. The particle is what we detect when the field is excited in a particular way. An electron is not a tiny hard bead that exists separately from the electron field. It is a small, definite excitation of that field, something like a ripple on an otherwise quiet surface. Though even that comparison should be handled gently because quantum fields are not made of water and do not ripple through ordinary space in the same visual way. Still, the ripple image is helpful if we do not push it too far. Imagine a calm lake. A ripple appears on it. You can point to the ripple, follow it, measure it, and describe how it moves. But the ripple is not a separate substance from the lake. It is a pattern in the lake. In a similar spirit, a particle can be thought of as a pattern or excitation in a field. The field is the underlying reality, and the particle is what happens when the field has a certain kind of localized activity. Remove the ripple, and the lake remains. Remove the particle, and the field remains in its quiet state. This is where the vacuum changes character. If fields exist everywhere, then a region with no particles is not a region with no fields. It is a region where the fields are not excited into detectable particles. The vacuum is the quiet condition of all those fields. It is not the absence of the stage. It is the stage before the actors appear, with the lighting grid, floorboards, curtains, ropes, wiring, and all the backstage machinery still quietly in place. Of course, a quantum field is not actually a theatre, and the universe has no stage manager with a clipboard, though sometimes that would be reassuring. The point is that empty space still contains the underlying field structure from which particles can arise and through which forces act. This idea can feel upside down because it reverses the order we naturally imagine. We tend to think particles come first and fields are something particles create around themselves. A charged particle creates an electric field, we might say. A magnet creates a magnetic field. A planet creates a gravitational field. That language works in many settings, but quantum field theory asks us to see fields as more basic. Particles do not own the fields. Particles are excitations of fields. The field is not merely a trail left behind by the particle. The particle is a particular activity of the field. The reason physicists take this view seriously is not because it sounds elegant, although it does have a certain neatness once you get used to it. They take it seriously because it works. Quantum field theory has produced some of the most precise predictions in all of science. It explains how particles are created and destroyed in high-energy experiments. It describes how light interacts with matter. It provides the framework for the standard model of particle physics, which organizes the known fundamental particles and their interactions. This is not a decorative metaphor. It is a practical working theory that has survived repeated experimental tests with remarkable success. One of the striking consequences is that the number of particles is not fixed in the way older physics might suggest. In everyday life, objects usually persist. A chair does not suddenly turn into 3 chairs because someone looked at it with scientific enthusiasm. A spoon remains a spoon unless a toddler, a dog, or a dishwasher gets involved. But at the quantum level, especially at high energies, particles can be created or absorbed. Light can produce particle pairs under the right conditions. Particles can emit other particles. Some unstable particles decay into different particles. Field theory handles this naturally because particles are excitations that can appear, disappear, and transform as the fields interact. The fields remain the underlying systems. This matters deeply for the vacuum because it means empty space is not a simple absence waiting for objects to be placed inside it. It is the baseline arrangement of fields capable of producing all the particles we observe. The vacuum is not made of electrons, photons, and quarks in the ordinary sense, because those are excitations. But the fields associated with them are present even when no actual particles are present. The vacuum is what those fields are doing when they're doing as little as quantum nature allows. That final phrase is important. Doing as little as quantum nature allows. In classical thinking, a field could be completely still. You could imagine all disturbances removed until nothing moves at all. But quantum theory does not permit the same kind of perfect stillness. The lowest energy condition of a field still has a kind of unavoidable uncertainty. It is not jiggling because something bumped it. It is not noisy because our instruments are poor. It is restless because the rules of quantum physics do not allow certain features to be pinned down with unlimited exactness. So even the vacuum, the quietest state, has subtle activity. This does not mean there is a hidden wind blowing through empty space. It does not mean the vacuum is a froth of tiny solid particles in a literal everyday sense. Many popular descriptions speak of particles popping in and out of existence, and that can be a useful image for beginners, but it should not be mistaken for a tiny fireworks show happening in the dark. Quantum fields are more subtle than that. The fluctuations of the vacuum are features of the field state itself. They affect what can be measured, how particles behave, and how forces show up in delicate experiments. They are real in their consequences, even if they do not look like a small crowd of miniature objects flashing on and off like faulty Christmas lights. The ocean metaphor is helpful here, but only if we keep it as a guide rather than a literal picture. An ocean fills a region. It can be calm or wavy. A wave is not separate from the ocean, but a behaviour of it. Different kinds of waves can exist in the same ocean. Yet quantum fields are not all one single water-like substance. The universe contains many fields, and each kind of particle corresponds to its own field or a related set of fields. These fields overlap in space without bumping into each other like ordinary fluids. They can interact, but not because they are thick liquids sloshing together. They interact according to the rules of quantum theory. Calling it an invisible ocean helps us relax into the idea that space is full of underlying physical presence, but the real picture is more precise and far stranger. One way to make this more concrete is to think about light. In a dark room, we might say there is no light. That does not mean the electromagnetic field has vanished from the room. It means the field is not excited in a way that produces visible photons reaching your eyes. Turn on a lamp, and the field carries energy outward as light. Turn it off, and the field returns to a quieter state. The field was not created by the lamp from absolute nothing. The lamp transferred energy into the field, creating excitations we experience as light. Darkness is not the non-existence of the electromagnetic field. It is the absence of visible light excitations. This is similar to how a vacuum is not the non-existence of fields, but the absence of particle excitations in those fields. The same idea applies to the electron field, though it is harder to picture. Electrons are not little pellets stored somewhere until needed. They are excitations of the electron field. Every electron in the universe is the same kind of excitation of the same field. This helps explain why electrons are identical. One electron is not manufactured with slightly different craftsmanship from another. Electrons do not come in artisanal batches. They have the same mass, the same charge, the same basic properties because they are excitations of the same underlying field. This is a very different view from imagining each electron as a tiny independent object with its own private identity. That sameness is one of the quiet clues that fields are fundamental. If particles were little separate mechanical objects, one might wonder why they are so perfectly alike. Why is every electron exactly like every other electron? Why does nature not produce slightly heavier electrons? slightly weaker electrons, electrons with a bit of personality and questionable punctuality. In quantum field theory, the answer is that an electron is a standard excitation of the electron field. Its properties come from the field and the way it interacts with other fields. The particle is not an individual machine built from smaller screws. It is a repeatable pattern in a universal field. Fields also help explain how particles can be created in collisions. In particle accelerators, scientists smash particles together at high energies. The result can be new particles that were not simply hiding inside the original ones like toys in a box. Energy from the collision excites fields, and those excitations appear as particles. It is less like breaking open a watch and finding new gears, and more like striking a drum and producing new vibrations, though again the drum image is only a loose guide. The fields allow energy to take the form of different particles under the right conditions. The vacuum is the quiet set of drums before anything is struck. If this makes reality sound less solid, that is because at its deepest known levels, solidity itself is an emergent experience. The table beside you feels solid because electromagnetic interactions between atoms resist the atoms in your hand. It is not solid in the sense of being perfectly filled all the way down with hard material. Atoms are mostly space by volume, but that does not make the table unreal or ghostly. The fields and forces involved give matter its structure. The familiar firmness of things comes from interactions among fields and particles, organized into atoms, molecules, and materials. The ordinary world is stable not because it is made of tiny classical bricks, but because quantum fields behave in consistent, rule-governed ways. This is why the vacuum can be physically important even though we do not feel it directly. Every particle that moves through space is really an excitation moving within a field framework. Every interaction depends on fields. The vacuum is the background state of those fields, and changing that state can change what particles are like. In some situations, the vacuum behaves differently than in others. Around strong fields, near boundaries, or under extreme conditions, the vacuum can reveal properties that are normally hidden. It is quiet in ordinary life, but not irrelevant. The Higgs field gives a famous example, though we will wander into it more carefully later. Unlike some fields whose excitations may be absent in the vacuum, the Higgs field has a non-zero presence even in empty space. This background condition is connected with why many particles have mass. That means the vacuum is not just where particles move. It helps determine what some particles are like. Empty space is involved in the basic properties of matter. That sentence may sound as if it has had too much late-night coffee, but it is one of the serious lessons of modern physics. The vacuum may also be connected with the large-scale behavior of the universe. Cosmologists study whether the energy of empty space contributes to the accelerated expansion of the cosmos. This leads to ideas such as dark energy and the cosmological constant, which we will approach later without trying to make anyone sit upright in alarm. The important point for now is that the vacuum is not limited to tiny laboratory effects. Its properties may matter across the largest distances. The emptier space between galaxy clusters may still influence the fate of the universe. There is a certain humility in this. For a long time, human beings naturally focused on visible things: stars, stones, bodies, rivers, fire. Then science showed that invisible air is a physical substance. Then it showed that invisible fields shape motion and light. Then quantum theory suggested that particles themselves are excitations of fields. At every step, the invisible became less like nothing and more like structure. The vacuum, once imagined as the removal of everything, became the quiet condition of the very fields from which everything can appear. This does not mean we should abandon the word particle. Particles are real in the sense that they are what detectors detect. A particle can leave a track in a chamber, deposit energy, be counted, scatter, decay, and trigger instruments. Physics does not say particles are imaginary. It says particles are not the deepest standalone ingredients in the old mechanical sense. They are field excitations with particle-like behavior when measured in the right way. The language we use depends on what we're studying. Sometimes particle language is perfect. Sometimes field language is necessary. nature is under no obligation to fit one comfortable image. It is a bit like describing the sea. If you're swimming, you may talk about waves hitting you. If you're studying climate, you may talk about currents and heat. If you're navigating, you may talk about tides and depth. All are real descriptions, but each serves a purpose. In quantum physics, particles and fields are different ways of talking about the same underlying systems, with fields often giving the more complete view. The vacuum belongs to that field view. It is what you get when the sea is as calm as it can be, not when the sea has disappeared. And because the fields are everywhere, the vacuum is everywhere too. It is not only in deep space, it is in the room around you, though the room is also full of air, light, dust, and the occasional personal possession pretending not to be clutter. Between the atoms of your walls, within the spaces of matter, across the gaps between planets, the fields are present. The vacuum state is easiest to think about when ordinary matter has been removed, but the underlying fields are not confined to special empty places. They are part of the fabric of the physical world. This can make the universe feel oddly intimate. The same electron field associated with electrons in distant galaxies is also associated with electrons in your body. The same electromagnetic field that carries starlight across space also carries the light from the screen or lamp near you. The fields do not stop at the edge of familiar objects. They extend throughout space, linking the local and the cosmic in one shared framework. The vacuum is not a lonely emptiness far away. It is the quiet baseline around and within everything. Of course, we should be careful not to turn this into mysticism. Quantum fields are not thoughts. They are not emotions. They are not a cosmic mood. They are mathematical and physical entities used to describe measurable phenomena. They are strange enough without being decorated beyond recognition. The beauty of the idea is not that it makes the universe vague, but that it makes it precise in a way our everyday imagination did not expect. It tells us that the emptiest possible space still has a defined physical state, and that particles are organized disturbances in fields that fill the universe. So when we speak of the invisible ocean of quantum fields, we are giving a gentle image to a serious scientific idea. Beneath the familiar world of objects and air and sound, there is a deeper description in which fields are present everywhere. Particles are their excitations. Forces are connected with their interactions. The vacuum is their quiet condition. This is why empty space can have effects. This is why removing matter does not remove physical structure. This is why the question of what the vacuum is made of leads not to a blank answer, but to the foundation of modern physics. And once that foundation is in place, the next strange idea becomes a little easier to approach. If the vacuum is the lowest energy state of quantum fields, and if quantum fields can never be perfectly still in the classical sense, then empty space is not only structured, it is subtly restless. Its stillness has texture. Its quiet has limits, not the restlessness of air molecules bouncing around, and not the noise of a hidden machine, but a quantum restlessness woven into the fields themselves. That is where the vacuum begins to behave less like an empty room, and more like a calm surface that trembles even when no wind is blowing. That quiet trembling beneath the surface of the vacuum is one of the reasons modern physics feels so different from the older mechanical picture of the world. In the older picture, if you removed every particle from a region and cooled everything as much as possible, you might expect perfect stillness. No motion, no light, no sound, no heat, no hidden activity. The universe, at least in that little region, would be like a room after the last candle has gone out and the final footstep has faded. But quantum physics does not quite allow that kind of absolute stillness. It leaves a faint, unavoidable restlessness in the fields themselves. Not a restlessness caused by air, dust, heat, or ordinary motion, but something built into the way nature behaves when we look at the smallest scales. This is where the phrase vacuum fluctuations enters the story. It sounds technical and perhaps a little dramatic, as though empty space is having tiny mood swings. But the basic idea is gentle enough. A quantum field, even in its lowest energy condition, cannot be perfectly frozen into complete certainty. There are always small variations in what the field is doing. These variations are not caused by bad measuring tools. They are not caused by particles sneaking into the experiment when no one is watching. They are part of the quantum nature of fields. The vacuum is the quietest state the fields can have, but quietest does not mean absolutely motionless. It means as calm as quantum rules permit. To see why that matters, it helps to begin with an everyday contrast. If you imagine a guitar string, you can picture it vibrating after it has been plucked. Eventually the sound fades. The string settles. In ordinary life, you might say it is now completely still. That is the classical picture. Energy was put into the string vibrated, the energy drained away into the surrounding air and the instrument, and now the string rests. But in quantum physics, systems do not always have permission to rest in the absolute way our imagination expects. The lowest possible state still contains a minimum kind of activity. It is not producing music, it is not loudly vibrating, but it is not the same as a perfectly dead line on a page. The universe refuses to become a completely rigid statue at its foundation. This idea appears first in simple quantum systems before we even get to the vacuum. A tiny system, such as an atom or a field mode, has limits on how quiet it can become. Even at the lowest possible energy, it retains what physicists call zero-point energy. The name sounds like it should mean no energy, which is a little unfair of the language, but it means the energy that remains at the lowest point. It is the baseline hum, the amount that cannot be removed. If ordinary heat is like lively movement in a room, 0-point energy is the floor beneath the room. You can quiet the party, turn off the music and send everyone home, but the floor is still there. This is not because nature is inefficient or because someone forgot to switch off the final lamp. It comes from the uncertainty at the heart of quantum theory. In everyday physics, we often imagine that an object can have a perfectly definite position and a perfectly definite motion at the same time. A marble on a table can be right there and not moving. A sleeping dog can occupy the rug with admirable certainty and very little ambition. But in quantum physics, certain pairs of properties cannot both be fixed with unlimited precision. If you try to make one perfectly definite, the other becomes less definite. For a field, this means you cannot make its value and its rate of change both perfectly settled everywhere. The result is a lowest state that still has fluctuations. That word fluctuations can be easy to misunderstand. In daily life, a fluctuation is usually something changing because of outside disturbance. A candle flame flickers because air moves around it. The surface of tea trembles because the table was nudged. Your patience fluctuates because someone is explaining the rules of a board game for the third time and still has not reached the part where anyone actually plays. But vacuum fluctuations are not like ordinary disturbances. They are not a sign that empty space has been shaken by something else. They are what remains even when outside disturbances are removed. They are intrinsic to the quantum vacuum. In field language, every field has possible ways of being excited. Some excitations correspond to particles. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. But even when no particle excitations are present, the field still has its ground state. That ground state is what we call the vacuum. The fluctuations are the subtle variations present in that ground state. They are not particles in the ordinary sense, and they are not little objects flying around. They are features of the field itself. This is one of those places where popular science often reaches for the image of particles popping in and out of existence. It is a memorable picture, and it can be useful for giving a quick impression that the vacuum is not empty. But if we take it too literally, it becomes misleading. Vacuum fluctuations are not simply tiny billiard balls appearing from nowhere, bouncing around for a moment, and then vanishing before the universe notices. The real description is more careful. Quantum fields have fluctuations in their lowest energy state, and in calculations, physicists sometimes describe certain effects using the language of virtual particles. But virtual particles are not the same as ordinary particles that a detector can catch and count. They are part of a mathematical way of describing interactions. They are useful, but not little ghosts with tiny passports stamping in and out of reality. So it is better, at least for now, to think of the vacuum as a field state with unavoidable uncertainty. The fields are present everywhere, and their quietest condition still has texture. This texture can influence real things. That is the crucial point. If vacuum fluctuations were only a strange idea in a notebook, we might file them away as one more oddity of theory. But they show up in physical effects that can be measured. They contribute to tiny shifts in the energy levels of atoms. They affect how particles interact. They help explain why certain processes happen the way they do. The vacuum is not loud, but it leaves fingerprints. One famous example involves the atom. According to early quantum theory, certain energy levels in hydrogen should have matched in a particular way, but careful measurements showed a tiny difference. This difference, known as the Lamb shift, could be explained by considering the interaction between the electron and the fluctuating electromagnetic field of the vacuum. In simple language, the electron in the atom is not sitting in a perfectly empty electromagnetic silence. It is influenced by the subtle quantum activity of the field around it. The effect is extremely small, but small does not mean unimportant. In physics, tiny differences can open enormous doors. Another related idea is spontaneous emission. An excited atom can release light and drop to a lower energy state. It may sound as if the atom simply decides to emit light on its own, like a very small lamp growing tired of suspense. But the quantum vacuum plays a role in how this process is understood. The electromagnetic field, even in its vacuum state, provides the background fluctuations with which the atom interacts. The atom is not sitting in an absolute nothing. It is coupled to fields that have a quantum ground state. This helps shape the timing and possibility of emission. Again, the vacuum is quiet, but it is not absent. There is also the Casimir effect, which we will come to more fully next. For now, it is enough to say that when two very close surfaces are placed in a vacuum, the allowed fluctuations of the electromagnetic field between them differ from those outside them. This difference can produce a tiny measurable force. Nothing in the old sense should not be able to push plates together. But the quantum vacuum is not nothing in that old sense. It has structure, and boundaries can change that structure. The result is one of the most elegant reminders that empty space has physical consequences. Now, it is worth pausing here because this subject can easily invite exaggerated claims. Vacuum fluctuations are real in the scientific sense that they are part of a tested framework and produce measurable effects. But they are not magic. They are not an unlimited energy source waiting to power cities. They do not allow us to borrow energy casually and ignore the rules of physics. They do not mean anything can appear from nothing in the ordinary everyday sense. The vacuum is strange enough without turning it into a cosmic vending machine. If empty space were that easy to exploit, engineers would have noticed, and your phone charger would probably be a small box labelled nothing battery, which would be both convenient and deeply suspicious. The reason we cannot simply drain energy from the vacuum is that the vacuum is already the lowest energy state of the fields under ordinary conditions. You cannot extract useful energy from a system that is already at its baseline without changing the conditions or putting something else into the setup. It is like trying to roll downhill from the lowest valley. You may have enthusiasm, but there is nowhere lower to go. Some situations can reveal differences in vacuum energy, especially when boundaries or external conditions are involved. But that is not the same as scooping free energy out of emptiness. The vacuum has effects, but it does not hand out miracles. This is important because the word energy can be tempting. Once people hear that the vacuum has energy, it is natural to imagine an invisible fuel. But energy in physics is not always fuel in the practical sense. A system can have energy that is not accessible for doing ordinary work. The ground state energy of quantum fields is part of their physical description, but it is not something we can simply plug into a kettle. The universe is very strict about these things, which is probably fortunate. A universe where teacups could suddenly harvest unlimited vacuum power might also be a universe where breakfast becomes unpredictable. The deeper significance of vacuum fluctuations is not that they give us easy energy, but that they show how empty space participates in physics. In the classical view, particles and forces did the work, while the vacuum was the empty background. In the quantum field view, the vacuum is a state of the fields, and the fields are the foundation for particles and forces. The vacuum can influence what happens because it is part of the system. It is not an idle void. It is the quietest condition of an active framework. The word restless is useful as long as we understand it carefully. The vacuum is not restless in the sense of having ordinary motion through time like waves on the sea. It is restless in the sense that quantum uncertainty prevents perfect stillness. If we could somehow zoom into the smallest descriptions of the field, we would not find a flat nothingness. We would find a state with fluctuations whose averages may look calm, but whose internal quantum character is not simply zero. The vacuum is stable, but not blank. It is calm, but not classically motionless. This difference between average calm and underlying fluctuation appears in many parts of physics. A surface can look smooth from far away and rough under a microscope. A room can feel silent while a sensitive instrument detects faint vibrations. A crowd can appear still from a balcony while each person shifts slightly in place. The vacuum is not exactly like any of these because quantum fluctuations are not ordinary hidden motion, but the comparisons help us avoid the mistake of thinking that calm means featureless. A thing can be quiet and still have structure. One particularly interesting point is that vacuum fluctuations are connected with probability. Quantum theory does not describe microscopic reality as a simple clockwork of definite little objects following exact paths in the old sense. Instead, it gives probabilities for possible outcomes. The vacuum state is not a state in which every field property has a perfectly sharp value. It is a state with definite overall features, but with fluctuations in measurable quantities. When physicists calculate what happens in experiments, those fluctuations help shape the probabilities of events. The vacuum is part of the statistical fabric of the quantum world. This is why precision experiments are so important. Quantum vacuum effects are often tiny, and detecting them requires careful instruments, clean conditions, and a great deal of patience. The effects do not announce themselves by rearranging furniture or tapping on the window. They appear as slight shifts, subtle forces, small corrections, patterns that match theory only when the vacuum is included. This is one of the beautiful habits of physics. The universe often whispers before it speaks loudly. A tiny discrepancy, measured with care, can reveal that a whole deeper layer exists beneath the obvious one. The vacuum also affects how we think about particles themselves. A particle moving through the vacuum is not moving through a passive emptiness. It interacts with fields, and those interactions can alter its observed properties. Physicists sometimes speak of particles being dressed by their interactions with the vacuum. The image is quite charming, as if an electron refuses to go out without its proper quantum coat. What it means is that the particle we observe includes not just a bare ideal object, but the effects of its interactions with surrounding fields. In quantum theory, nothing is completely isolated in the way classical imagination might prefer. The vacuum is part of the particle's environment, even when that environment contains no ordinary matter. This interconnectedness can feel surprising, but it is also consistent with the field picture we have been building. If fields are everywhere, then no particle is truly separate from the field framework. The vacuum is the lower state of that framework, and particles are excitations within it. The boundary between a particle and the vacuum is not like the boundary between a pebble and an empty box. It is more subtle, more relational. A particle is what the field is doing in a certain way, and the vacuum is what the field is doing in its quietest way. Interactions between them are not optional extras. They are part of the theory. At this point, the vacuum may seem almost too lively. We began with nothing, and now it has fields, fluctuations, energy, effects on atoms, influence on emission, and a role in particle behavior. One might reasonably ask whether physicists have simply redefined nothing until it means something. In a way, yes, but not carelessly. Science often refines everyday words because nature does not obey our casual categories. Empty space in ordinary language means no ordinary stuff. The quantum vacuum in physics means the lowest energy state of quantum fields. These are different meanings. The confusion comes only when we expect one word to do all the work. It is not wrong to call a vacuum empty. It is empty of particles in a particular sense. It is empty of air in a laboratory sense. It is empty of ordinary matter in a cosmic sense. But it is not empty of physical structure. It is not empty of fields. It is not empty of quantum uncertainty. It is not empty of consequences. It is an emptiness with rules. There is something very steadying about that idea. The universe is not chaotic nonsense beneath the surface. It is strange, but disciplined. Vacuum fluctuations are not random magic. They follow precise quantum laws. They can be calculated, tested, and compared with experiment. Their existence does not mean anything can happen. It means that what we call nothing has a lawful microscopic character. Empty space is not a loophole in reality. It is part of reality's order. And because it is part of that order, it connects the smallest scales to the largest questions. On tiny scales, vacuum fluctuations affect atoms and particles. In more speculative and difficult areas, physicists ask how vacuum energy relates to gravity and the expansion of the universe. This connection is not fully understood. In fact, it leads to one of the great puzzles of modern physics, because the vacuum energy expected from quantum fields and the vacuum energy suggested by cosmology do not line up in any simple way. We do not need to solve that puzzle tonight, which is fortunate because many extremely awake people have tried, but it is enough to notice that the vacuum is not a side issue. It sits at the crossroads of quantum theory, particle physics, and cosmology. So the restless stillness beneath reality is not a poetic decoration. It is a real shift in our understanding of what empty space means. Classical emptiness was a blank background. Quantum emptiness is a ground state with fluctuations. It is the softest possible murmur of fields that cannot be made completely silent. It is the quiet from which particles can be excited, the background that influences atoms, the condition that changes near boundaries, the baseline whose properties may shape the cosmos. As you imagine the space around you now, the air in the room, the darkness beyond the walls, the vast distances between stars, it may help to hold two thoughts at once. At the scale of daily life, empty space is empty enough. The room is not secretly buzzing in a way you need to worry about. Your blanket is not floating on a storm of tiny visible particles leaping from nothing. But at the deeper quantum level, the vacuum is not a dead void. It has a kind of unavoidable texture, a minimum uncertainty, a quiet activity that belongs to the fields themselves. The stillness is real, but it is not simple. And once this idea is in place, another familiar phrase begins to make more sense, though it also needs careful handling. People often say that quantum physics allows particles to borrow energy from the vacuum for a brief moment, or that virtual particles appear and disappear in empty space. These images are common because they gesture towards something true, but they can easily drift into misunderstanding if we let them become too literal. So the next step is to take those tiny imaginary accountants of the vacuum, those so-called virtual particles and borrowed energies, and ask what physicists actually mean when they speak that way, and why nature's quiet bookkeeping is subtler than it first sounds. The language of virtual particles is one of those places where physics becomes both wonderfully useful and unusually easy to misread. It gives us a way to talk about interactions in the quantum vacuum, and it appears in explanations of forces, particle behavior, and the restless quality of empty space. But it also creates images that can become a little too vivid. Once someone hears that particles appear and disappear from nothing, it is natural to picture empty space like a tiny stage magician, pulling rabbits from invisible hats and then quietly putting them back before anyone checks the cage. That image is memorable, but it can lead us away from what physicists actually mean. The real idea is subtler, more careful, and in some ways even stranger. A good place to begin is with the word virtual. In everyday speech, virtual often means almost real, or simulated, or existing in a computer rather than in the physical world. A virtual meeting is not quite the same as sitting together in one room, though it can still be very real when someone forgets to mute themselves. In physics, virtual has a different meaning. A virtual particle is not simply an ordinary particle that appears for a brief moment and then vanishes. It is not a tiny object that a detector could directly catch during its short visit. Instead, virtual particles are elements in a mathematical method used to describe interactions among quantum fields. They are internal pieces of the calculation, not free particles travelling through space in the same way as a photon from a lamp or an electron in a detector. This distinction matters because ordinary particles, the kind physicists can detect as final products of an experiment, obey the usual rules for real measurable particles. They can carry definite energy and momentum in the right combinations. They can leave tracks, deposit energy, trigger instruments, and arrive as actual outcomes. Virtual particles do not appear as final detectable things in that direct way. They exist inside the bookkeeping of an interaction. They help describe how one particle influences another, how forces are transmitted, and how quantum fields respond. They are not imaginary in the sense of useless or fake, because calculations using them match real experiments with astonishing precision. But they are not real in the same way as ordinary particles you can count at the end of a collision. One way to approach this gently is to think about a conversation. Suppose two people are speaking across a table. You can hear the words that arrive at your ears. Those words are real events in the air. But behind the conversation there are many hidden processes. Thoughts forming, memories being selected, tiny hesitations, changes of expression, adjustments in tone. If you wrote a detailed analysis of the conversation, you might include all sorts of internal steps that help explain the final exchange, even though no one in the room could point to a single little object called a hesitation packet flying from one person to the other. Virtual particles are not thoughts, of course, but the comparison helps. They are part of the internal description of how an interaction unfolds, not the same as the directly observed outcome. In quantum field theory, physicists often use diagrams to organize calculations. These diagrams are commonly associated with Richard Feynman, who helped develop a powerful visual method for dealing with particle interactions. The diagrams look simple enough, almost like little sketches of lines meeting and branching, which is probably one reason they have become famous outside physics. But they are not literal cartoons of tiny particles following exact paths. They are a compact way to represent terms in a calculation. External lines can correspond to real incoming and outgoing particles. Internal lines correspond to virtual particles. Those internal lines help account for the ways quantum fields can interact during the process. For example, when two electrons repel each other, the older picture might say that each electron creates an electric field, and the field pushes the other electron away. That is still a useful description in many settings. In quantum field language, the interaction can be described as the exchange of virtual photons. This does not mean the electrons are tossing tiny balls of light back and forth, like a microscopic game of catch. It means that the electromagnetic field mediates the interaction, and in the calculation the internal exchange is represented by virtual photons. The force is real. The repulsion is real. The virtual photon is a way of describing the interaction within the quantum field framework. This is one of the reasons virtual particles are so useful. They give physicists a language for forces that fits naturally into quantum theory. Electromagnetic interactions can be described through photons. The strong nuclear force can be described through gluons. The weak force involves other force-carrying particles. In ordinary detectable situations, these particles can sometimes be real. Light is made of real photons. But inside interactions, the corresponding virtual particles do not have to behave like free detectable particles. They are allowed to appear in intermediate steps of the calculation in ways that would not make sense for particles travelling freely to a detector. They are part of the internal structure of the process. This brings us to the idea of borrowed energy, another phrase that is memorable and risky. You may have heard that quantum particles can borrow energy from the vacuum as long as they pay it back quickly. It sounds charming, as if the universe runs a very strict little bank with tiny clerks stamping forms in the dark. The idea is meant to gesture toward a real feature of quantum theory, but it can easily be misunderstood. Energy conservation is not casually suspended because the universe is feeling generous. Physics does not allow particles to simply take energy from nowhere and then hope no one checks. The deeper story has to do with uncertainty and the way intermediate states in quantum calculations are handled. In quantum theory, there are limits to how sharply certain quantities can be defined over very short intervals. This is sometimes loosely explained as allowing temporary energy fluctuations. In calculations, virtual particles can appear in intermediate steps without satisfying the same energy relation required for real particles. But this should not be imagined as a literal violation of energy conservation happening in the physical world. The full interaction obeys conservation laws. The starting conditions and final outcomes balance properly. The apparent looseness belongs to the internal mathematical description, not to a cosmic loophole that lets something come from nothing whenever it likes. A household comparison may help, though as always with quantum physics, it must be treated as a comparison, not a perfect picture. Imagine balancing a complicated set of accounts for a business. During the process, you might write temporary entries, estimates, adjustments, and internal transfers that do not represent final money in someone's pocket. They help you organize the calculation. At the end, the books must balance. If the final accounts do not balance, something is wrong. Virtual particles are somewhat like temporary entries in the accounting of quantum interactions. They are essential to getting the right final result, but they are not the same as final observed particles. Nature's tiny accounting tricks are not fraud. They are a precise way of keeping track of all the possible contributions to an interaction. This is why the phrase borrowed energy can be useful only if it is handled carefully. It suggests that the vacuum has temporary activity, and that quantum processes include possibilities that classical physics would not allow in a simple mechanical picture. But it should not suggest that energy conservation is optional. In real experiments, energy is conserved in the full physical process. The vacuum does not hand out energy like spare change. If you want to create real particles that can be detected, you need to supply real energy. High-energy collisions in particle accelerators can create new particles because the collision energy is available to excite the fields. The particles do not appear for free. They are paid for, so to speak, by the energy put into the system. The difference between virtual and real particles is especially important when we talk about the vacuum. Popular accounts sometimes say that the vacuum is full of virtual particle pairs constantly appearing and annihilating. This picture can be helpful as a quick sketch, because it suggests that empty space is not inert. But taken too literally, it makes the vacuum sound like a crowded gas of tiny particles flashing in and out. That is not the best way to think about it. The vacuum is the lowest energy state of quantum fields. It has fluctuations. Those fluctuations can be represented in certain calculations using virtual particles. But the vacuum is not simply full of little ordinary particles that happen to disappear before we can catch them. A detector placed in an ideal vacuum does not simply click endlessly, because virtual particles are flying into it. If it did, vacuum physics would be rather easier to demonstrate, and laboratories would be filled with very confused graduate students asking the detector to calm down. Virtual particles are not directly detected because they are not free particles in the usual sense. Their reality is indirect, tied to the measurable effects they help calculate. We infer the structure of the vacuum and the role of these internal processes from their consequences, not from catching virtual particles one by one in a jar. This indirect reality is common in science. Many things are known through effects rather than direct appearance. You do not see air pressure itself, but you see what it does to a barometer or a balloon. You do not see a magnetic field directly, but you see a compass turn or iron filings arrange themselves. In quantum field theory, virtual particles are part of a successful framework that predicts measurable outcomes. They are not visible objects, but they are not meaningless either. They sit in that careful space between calculation and physical consequence, which is why physicists use them while also warning people not to picture them too literally. A useful example comes from the force between charged particles. If two electrons repel, we can calculate that repulsion using virtual photons. The virtual photons are not observed as flashes of light between the electrons. They are internal carriers of the interaction in the calculation. Yet the resulting force is measurable. The electrons move as predicted. The theory works. So the virtual photon is not a little light particle you can photograph, but it is part of the best description of how the electromagnetic field produces the interaction. The language is strange because the quantum world does not divide neatly into everyday categories of real object and mere idea. Another example appears in the way particle properties are affected by interactions with the vacuum. An electron is not simply a bare point-like object sitting alone. It is surrounded, in a quantum sense, by the effects of its interactions with fields. These effects alter the measured properties of the electron. Physicists sometimes describe this as the electron being dressed by a cloud of virtual particles. The word cloud is again a metaphor, but it points to something important. The electron we observe includes the influence of interactions with the vacuum. This helps explain why extremely precise measurements, such as those involving the magnetic behavior of the electron, agree with quantum field theory only when these subtle effects are included. The success of these calculations is one of the most impressive achievements in physics. In some cases, theory and experiment match to extraordinary precision. That is not because physicists were lucky with a colourful metaphor. It is because the mathematical structure of quantum field theory captures something real about how nature behaves. Virtual particles, when used properly, are part of that structure. They're tools that allow physicists to calculate the contributions of quantum fields to interactions. They are not optional storytelling decorations, but they are also not tiny ordinary objects living secret lives in the vacuum. There is a nice practical lesson here about scientific language. Sometimes a phrase survives because it is useful, even if it is not perfectly literal. The sun rises, we say, even though Earth is rotating. A vacuum cleaner sucks, we say, even though air pressure does much of the pushing. Virtual particles appear and disappear, we say, even though the precise meaning lies in the formalism of quantum fields. These phrases are not wrong in every context, but they must be unpacked when we want deeper understanding. Science often begins with simple language and then gently asks us to revise what the language means. The vacuum, viewed through this lens, becomes less like a container full of ghost particles and more like a complex ground state whose behavior can be explored through interactions. When particles move through it, they are affected by the fields and their quantum properties. When boundaries are placed in it, the allowed field fluctuations can change. When high-energy processes occur, the fields can be excited into real particles. Virtual particles are one of the ways physicists account for the possible intermediate contributions that shape these processes. They are nature's bookkeeping entries, and the final page still has to balance. This also helps explain why the vacuum can influence forces without being a material in the ordinary sense. In classical physics, a force often feels like something must be pushing or pulling directly. But quantum field theory describes interactions through field exchanges and probabilities. A force can arise because fields interact in certain ways, and virtual particles can represent those interactions mathematically. The vacuum is not doing this as a substance with little hands. It is the field structure itself that allows interactions to occur. The vacuum is not an empty hallway between particles. It is part of the field system in which particles and forces are defined. The idea of borrowed energy can also be softened by remembering that quantum physics does not describe the microscopic world as a single fixed route from beginning to end. Instead, it often requires considering many possible contributions to a process. Some of those contributions are more important than others. Some are highly unlikely, but still influence the final result in tiny ways. The calculation adds them together according to strict rules. Virtual particles appear as internal features of these possible contributions. They do not represent a little film of what definitely happened. They represent possible intermediate structures that together determine what can be measured. This is deeply different from everyday causality. If a mug falls from a table and breaks, you can usually tell a simple story. It was on the table, it tipped, it fell, it hit the floor, it broke, and someone sighed. Quantum interactions do not always permit that kind of single classical story. The theory gives a way to compute the probability of outcomes, and the internal steps of that computation do not necessarily correspond to one definite path that reality secretly followed. Virtual particles belong to that quantum accounting. They help calculate the result, but they are not a hidden movie of little objects travelling between events. Forces themselves become more subtle in this picture. Take the electromagnetic force. In everyday life, it is responsible for light, electricity, magnetism, chemistry, the structure of atoms, and the fact that your hand does not pass through the table. In field theory, the electromagnetic field is always present, and interactions involving charged particles can be described in terms of photon exchange. Real photons are light. Virtual photons are internal mediators of electromagnetic interactions. The same field underlies both. This is one of the strengths of the theory. It unifies radiation and force in a single framework. The strong and weak nuclear interactions have their own field descriptions and their own internal exchange particles. The strong force binds quarks inside protons and neutrons and helps hold atomic nuclei together. The weak force is involved in certain kinds of radioactive decay and in processes inside stars. These are not everyday forces in the same way gravity and magnetism feel familiar, but they shape the matter from which the familiar world is made. Virtual particles appear in the calculations of these interactions too, again as internal features rather than directly observed final particles. Even when no real particles are present, the vacuum still contains the fields associated with these possibilities. That does not mean every possible particle is literally waiting in a tiny hidden cupboard. It means the fields have a ground state, and excitations of those fields can become particles when conditions allow. Energy can be transferred into a field and appear as real particles. Interactions can be described with virtual particles. The vacuum is the baseline from which these activities are described. This is why particle creation does not mean creation from absolute nothing. When real particles are produced in a collider, they arise from energy supplied by the collision and from fields that already exist as part of the physical framework. When radiation near strong fields leads to particle production, the energy comes from the field or the environment. In cosmology, there are discussions of particle creation in expanding space. But even there the subject is about fields in a changing space-time, not ordinary objects popping out of philosophical nothingness. Physics is not saying that nothing, in the absolute sense, casually becomes something. It is saying that the vacuum of quantum fields is not the same as absolute nothing. This distinction keeps us from overstating the mystery while still respecting it. The vacuum is strange, but it is not nonsense. Virtual particles are useful, but not tiny ghosts. Borrowed energy is a metaphor, not permission to break conservation laws. Quantum fluctuations are real, but not a swarm of free particles. The world beneath ordinary matter is subtle, but it is also disciplined. It has rules so reliable that we can build experiments around them, test them to astonishing precision, and use them to explain the behaviour of matter and light. The accounting trick, if we want to call it that, is not a cheat. It is a different kind of bookkeeping suited to a universe made of quantum fields. In ordinary accounting, you track coins or bills or numbers in a bank. In quantum field theory, you track probabilities, amplitudes, interactions, and allowed contributions. Virtual particles appear inside that tracking. They help physicists account for how a process can unfold according to the rules of the fields, and at the end, the measurable result must agree with conservation laws, symmetries, and experiment. Nature's books are not loose. They are almost frighteningly precise. There is something calming in that precision. The vacuum may be restless, but it is not chaotic. It may allow subtle intermediate possibilities, but it does not abandon order. It may be full of field fluctuations, but those fluctuations follow mathematical structure. The emptiest state of space is not a place where anything goes. It is a lawful condition, one whose effect can be measured in tiny shifts, delicate forces, and the detailed behavior of particles. This brings us toward one of the clearest places where the vacuum's hidden structure becomes physically noticeable. If the vacuum fluctuations of a field can be altered by boundaries, then placing objects close together in empty space can change the allowed patterns of those fluctuations. That change can produce a real force between the objects, not because air is pushing them, not because ordinary particles are streaming between them, but because the vacuum state itself is different in the space between them than it is outside. It is one thing to say that virtual particles are useful in calculations, and that vacuum fluctuations have effects. It is another to watch empty space seem to gently press two surfaces together, which is exactly where the story now begins to lean toward the Casimir effect. The Casimir effect is one of those experiments that sounds almost too delicate to belong to the same universe as planets, storms, and falling apples. It does not begin with a roaring accelerator, a telescope pointed into deep space, or a spectacular flash of energy. It begins with two objects placed extremely close together in a vacuum, so close that the gap between them is tiny compared with anything we normally handle. Then, if the conditions are controlled carefully enough, those objects feel a small force drawing them toward each other. Not because of air pressure, since the air has been removed, not because of glue, not because of static electricity, if the experiment has been designed properly. Not because tiny ordinary particles are rushing around like invisible billiard balls. The force appears because the vacuum itself, the quiet state of the fields, has been changed by the presence of the boundaries. That is the surprising heart of the Casimir effect. It shows that empty space is not simply a passive blank. It can respond to the shapes placed inside it. The vacuum between two closely spaced surfaces is not quite the same as the vacuum outside them. That difference creates a pressure, a tiny push, or more carefully, a difference in force that nudges the surfaces together. It is a measured physical effect, not just a decorative thought experiment. It is one of the clearest ways nature tells us that the vacuum has structure. The idea was proposed by the Dutch physicist Hendrik Casimir in the 20th century, while he was studying quantum theory and the behavior of electromagnetic fields. The basic setup is often described with two parallel conducting plates placed very close together in a vacuum. The plates are uncharged, which matters because otherwise ordinary electric attraction would confuse the result. In the simplified picture, the plates act as boundaries for the electromagnetic field. They restrict which field patterns can fit in the space between them. Outside the plates, more patterns are possible. Because the vacuum fluctuations of the field depend on which patterns are allowed, the vacuum state between the plates differs from the vacuum outside. The result is a small net force pressing the plates together. This may sound like saying nothing has fewer ways to be nothing in one place than another, which is exactly the sort of sentence that makes physics both beautiful and mildly impolite. But the meaning can be made more grounded. Think about sound in a room. A musical note depends on vibrations that fit the space where they occur. A long pipe can support certain tones. A short pipe supports different tones. A guitar string fixed at both ends can vibrate only in certain patterns. It cannot vibrate in just any shape it likes, because the ends hold it in place. The boundary conditions decide which vibrations are allowed. Quantum fields also have allowed patterns, and boundaries can restrict them. In the Casimir effect, the plates restrict the allowed electromagnetic field fluctuations in the narrow gap between them. Of course, the vacuum fluctuations are not ordinary sound waves, and the plates are not a musical instrument in the everyday sense. No one is plucking empty space and hearing a note. The comparison is only meant to show how boundaries change possible patterns. If a field exists everywhere, then placing conducting surfaces into space can alter the field's allowed modes nearby. The vacuum is the lowest energy state of the field, but that lowest state depends on the conditions imposed on it. Change the boundaries, and the vacuum state changes. The plates do not create the vacuum fluctuations, they shape them. The easiest image is to imagine two calm regions, one inside the narrow gap and one outside. Inside the gap, only certain field fluctuations can fit comfortably. Outside, there is more room and a broader range of possible fluctuations. This imbalance creates a net effect. The outside vacuum, in a loose sense, has more allowed fluctuations pressing than the inside gap. The plates are pushed toward each other. That wording is not perfectly exact, because the real calculation is more subtle than little waves physically pushing like wind. But as a gentle picture, it helps explain why the force is attractive in the classic setup. The important part is that the plates alter the vacuum field conditions, and the resulting energy difference produces a force. This is a remarkable idea because it turns emptiness into something that can be engineered. Not engineered in the sense that you can build a vacuum engine from nothing and use it to make tea, which would be convenient but not presently offered by the universe. Engineered in the sense that the shape, material and spacing of objects can affect the vacuum field around them. The vacuum has no ordinary substance to grab, yet its state depends on physical boundaries. That is not how a true philosophical nothing should behave. Nothing should not care whether two plates are close together. The quantum vacuum does care because it is not nothing. It is a physical state of fields. The force is extremely small at ordinary distances. You do not notice your furniture being pulled together by vacuum effects across the room. Your socks do not vanish under the bed because the quantum vacuum has developed an opinion about laundry. The Casimir force becomes significant only when objects are brought extremely close together, at scales far smaller than a grain of dust. At those distances, the vacuum effect can become measurable, and even important for tiny machines. In the world of microtechnology and nanotechnology, where parts can be separated by very small gaps, Casimir forces can affect how components move or stick. A force that is irrelevant for a chair may become a real engineering concern for a microscopic device. This is one of the recurring lessons of physics. Scale matters. A force can be invisible in daily life and decisive in a tiny system. Gravity dominates planets, moons, and falling apples, but it's almost irrelevant between small particles compared with electric forces. Surface tension barely matters to us when we walk through a doorway, but it matters enormously to insects standing on water. The Casimir effect belongs to the realm where small distances reveal the vacuum's subtle properties. It is not a household force, but it is real. The experiment itself is difficult because the force is so tiny and because other effects can easily hide it. Real plates are not perfectly smooth. They are not infinite. They may have tiny electrical patches on their surfaces. They may be affected by temperature. They may not be perfectly parallel. Dust, vibration, residual gas and material properties all matter. Measuring the Casimir effect is not like placing two dinner plates on a table and waiting for them to slide together while you nod knowingly. It requires careful design, sensitive instruments, and a deep understanding of every possible source of error. But over time, experiments have confirmed the effect in various forms with increasing precision. This is important because the Casimir effect is often presented as proof that virtual particles are real in the everyday sense. That statement is too simple. The effect is real. The force is real. The quantum field description that predicts it is real in the scientific sense of matching measurement. but saying it proves that ordinary little particles are popping in and out between the plates is not quite right. The Casimir effect can be calculated in different but equivalent ways. One way emphasizes vacuum fluctuations and allowed modes of the electromagnetic field. Another way can describe the force in terms of interactions between charges and currents in the plates. Both approaches are part of quantum field theory. The deepest lesson is not that we have photographed virtual particles, but that quantum fields and their ground states have measurable consequences. This kind of caution is useful because the vacuum attracts dramatic language. It is tempting to say that nothing pushes. The phrase is memorable and it captures the surprise. But what really pushes is the difference in the quantum field state caused by the boundaries. The plates change the allowed electromagnetic behavior in the gap. That produces a force. Empty space is not acting like a little hand. It is not a hidden gas blowing from outside. It is not a secret pressure of tiny marbles. It is the field structure responding to geometry and material conditions. The effect is less like wind pressing on a sail and more like the energy of the field configuration depending on the arrangement of the plates. A useful everyday analogy is a stretched sheet, though again it is only an analogy. If you place objects on a flexible sheet, the shape of the sheet changes, and the objects may move because the energy of the sheet changes with their positions. The objects are not pushed by an invisible person. They move because the system has a lower energy arrangement. In the Casimir effect, the field state and the boundaries form a system. The energy associated with that system depends on the separation between the surfaces. A force appears because systems tend to respond to energy differences. This is not magic, it is physical bookkeeping, though the account is written in quantum field language rather than ordinary mechanical terms. The original Casimir setup uses conducting plates, because conductors impose strong conditions on the electromagnetic field. In real life, materials are not perfect conductors, and the exact force depends on their properties. Different materials, shapes, and environments can change the effect. Scientists have studied Casimir forces between a sphere and a plate, between patterned surfaces and in fluids. In some arrangements, related forces can even become repulsive rather than attractive, depending on materials and medium. This does not overturn the basic idea. It shows that the vacuum and the surrounding conditions form a more flexible physical system than the simplest picture suggests. Temperature also matters. At absolute cold in the idealized theory, the vacuum fluctuations dominate the description. At non-zero temperatures, thermal fluctuations can contribute as well. In ordinary experiments, the distinction between quantum vacuum effects and thermal effects must be handled carefully. The real world never gives scientists the pure textbook version without asking for corrections. It adds roughness, temperature, finite size, impurities, and all the tiny inconveniences that make experimental physics both difficult and admirable. Still, the underlying effect remains one of the best-known demonstrations that boundaries can alter field fluctuations and produce measurable forces. There is something pleasing about the smallness of it. The Casimir effect does not need to shout. It does not bend starlight around galaxies or smash particles into showers of debris. It sits quietly at the edge of measurability, between surfaces separated by almost unimaginably small gaps, and tells us that the vacuum is not a neutral absence. The lesson is modest in scale but enormous in meaning. If empty space were truly featureless, there would be no allowed modes to change, no energy difference to calculate, no tiny attraction to measure. The fact that the effect exists means that the vacuum has physical content. This is one reason the Casimir effect is often used as a doorway into quantum field theory. It lets us talk about the vacuum without beginning with the most advanced mathematics. 2 plates, a tiny gap, a measurable force. That is enough to show that the vacuum behaves differently depending on boundaries. The picture is simple enough to hold in the mind, even if the full theory behind it is rich and technical. It gives the vacuum a kind of experimental handle. We cannot scoop the vacuum into a spoon, but we can arrange surfaces and measure what happens. It also helps us understand why the word empty must be treated carefully. The space between the plates is empty of air. It may be empty of ordinary particles. It may be shielded and cleaned and controlled. But it is not empty of the electromagnetic field. The field's vacuum state is still there, and the plates affect it. This is the same layered idea we have been building all along. Airless space is not absolute nothing. Particle-free space is not field-free. Field quietness is not classical stillness. The Casimir effect is what happens when that quietness is shaped by matter. Notice the subtle partnership between matter and vacuum here. The plates are made of matter. Their surfaces impose conditions. The vacuum field responds. The result is a force on the matter. Matter shapes the vacuum and the vacuum pushes back. This is not a violent push. It is small, delicate, and usually hidden, but conceptually it is important. It means that matter and empty space are not entirely separate categories. They interact through fields. The boundary between the thing and the nothing around it becomes less absolute. This is very different from the old container picture. In the old picture, space is the box and matter is the content. Remove matter from part of the box and that part simply contains nothing. The Casimir effect belongs to a newer picture, where fields fill the box, matter changes the field conditions, and the vacuum state itself contributes to physical behavior. Space is not just the box. It has field structure. Matter is not just placed inside it. Matter participates in shaping it. There is a quiet connection here to other parts of physics. In atoms, vacuum fluctuations affect energy levels. Near conducting plates, they affect forces. In particle physics, interactions with fields affect measured particle properties. In cosmology, vacuum energy may influence the expansion of the universe. These are not all the same phenomenon in a simple everyday sense, and we should not flatten them into one vague statement that the vacuum does everything. But they share a deep theme. The vacuum is not a dead background. It is a physical state whose properties matter. For bedtime purposes, we can keep the Casimir effect in a calm and accurate image. Imagine two tiny surfaces brought very close together in a carefully prepared vacuum. The air's gone. Ordinary disturbances are reduced. The space between them seems empty. Yet the electromagnetic field in its vacuum state still has allowed patterns, and the boundaries created by the surfaces restrict those patterns in the gap. Outside the gap, the field has different possibilities. That difference creates a tiny attraction. The plates move, not because nothing has become a substance, but because empty space is the quiet state of fields, and fields are sensitive to boundaries. The word gentle fits the effect well. The force is not large. It is not something that grabs macroscopic objects in daily life. It does not make space feel sticky around us, but at very small separations it can be strong enough to matter. Engineers working with tiny moving parts must sometimes consider it because surfaces can cling together. In this way, a deep quantum effect becomes a practical concern. The vacuum, usually treated as background, enters the workshop. This is a lovely reminder that modern physics is not only about distant galaxies or invisible equations. It can show up in devices, surfaces, materials, and measurements made in carefully controlled rooms. The same quantum field ideas that describe the vacuum between plates also belong to the broader framework used to understand light, matter, and particle interactions. The Casimir effect is small, but it is connected to the same theory that helps explain the structure of the physical world. There is also a philosophical charm in the effect. For centuries, people wondered whether empty space could exist. Then scientists learned to make vacuums by removing air. Later, quantum theory revealed that even particle-free space has field structure. The Casimir effect gives that structure a kind of touch. It says that under the right conditions, the vacuum is not only an idea in the mind, it can influence the motion of real objects. It can be measured with instruments. It can become part of an experimental result. The old void has become a participant. At the same time, we should not let the phrase "nothing pushes" become too grand. The Casimir effect does not prove that the vacuum is a material fluid. It does not prove unlimited energy is available from empty space. It does not mean that every gap contains a dramatic hidden pressure waiting to burst forth. It shows something more precise and more useful. Quantum fields have vacuum states. Boundaries alter those states. Changes in field energy can produce forces. That is enough. It is a deep result without needing exaggeration. The difference between exaggeration and wonder is important. Exaggeration makes the vacuum sound like a magic trick. Wonder lets it remain a scientific discovery. The real Casimir effect is wonderful because it is careful, measurable, and conceptually strange. It brings together quantum uncertainty, field theory, material boundaries, and precision measurement. It turns a quiet gap into a laboratory for the nature of empty space. It reminds us that reality can be subtle without becoming unscientific. As the story continues, the vacuum becomes even more surprising. So far, we have treated it mainly as the quiet state of fields that still fluctuate and respond to boundaries. But one field in particular changes the meaning of the vacuum in a different way. The Higgs field is not just another field that can be excited into particles. Its vacuum state has a special background presence throughout space. That presence affects many other particles, giving them a kind of resistance to acceleration that we experience as mass. In that sense, empty space is not only restless and responsive, it helps determine why matter has the properties it does. The vacuum does not merely sit around particles. For many of them, it is part of the reason they behave like matter at all. The small force between close surfaces showed us that the vacuum is not merely a blank gap. It can be shaped by boundaries, and it can answer with a measurable effect. But the vacuum has another role that reaches even deeper into the ordinary world, because it is tied not only to tiny pushes between plates, but to the mass of matter itself. This is where the Higgs field enters, and it changes the story in a quiet but profound way. So far, we have been imagining the vacuum as the lowest energy state of many fields, a calm condition that still carries quantum restlessness. The Higgs field adds something more. Its quietest state is not empty in the sense of being neutral or inactive. It has a steady background presence throughout space, and many particles are changed simply by existing within it. This is a strange idea, so it's best not to rush it. In everyday life, mass feels like one of the most basic facts about an object. A feather has a little mass, a stone has more. A suitcase on the final day of a trip has somehow gained mass in a way that feels personally unfair. We use mass to describe how much matter something contains and how hard it is to accelerate. Push an empty shopping cart and it moves easily. Push a loaded one and it resists more. That resistance is closely connected with mass. It is not exactly the same as weight, because weight depends on gravity, while mass belongs to the object itself. A suitcase would weigh less on the moon, but it would still have the same mass, and if you tried to shove it sideways, it would still resist being accelerated. The moon is kind, but not that kind. For a long time, mass was treated almost as a given. Particles had mass because that was one of their properties. An electron had its mass, a quark had its mass, other particles had theirs, and the job of physics was to measure these values and understand how particles behaved. But as physicists developed deeper theories of fundamental particles and forces, a difficulty appeared. The rules that described certain forces worked beautifully only if some particles started out as though they had no mass. Yet the real particles in the world clearly did have mass. Something had to explain how the theory could preserve its elegant structure while still giving particles the masses we observe. The answer became the Higgs field. The Higgs field is a quantum field, like the fields we have been discussing, but with a special feature. In the vacuum, even when no Higgs particles are present, the Higgs field does not settle to a completely neutral value. It has a constant background value spread through space. In ordinary language, empty space is filled with the Higgs field in its settled condition. This does not mean space is filled with a thick material or a gas or a sticky fluid. It does not mean there is a substance slowing everything down like honey. It means that the lowest energy state of the Higgs field has a presence that other fields can interact with. That interaction gives many fundamental particles their mass. The usual comparison is to imagine moving through a room full of something that affects how you move. But we have to be careful because the Higgs field is not a real liquid and mass is not ordinary friction. If a particle were being slowed by a medium, it would gradually lose energy, the way a swimmer loses speed in water. That is not what the Higgs field does. A particle moving through empty space does not slow down because of the Higgs field. Instead, the field changes the particle's basic relationship with motion. It gives the particle inertia, the resistance to being accelerated. Once a particle is moving, it can continue moving freely. The Higgs field does not drag it to a stop. It helps define how hard it is to change its motion. A calmer analogy is a little closer. Imagine a room where different guests receive different kinds of attention as they pass through. Someone unknown crosses easily, barely noticed. Someone famous enters and people gather round, slowing the person's ability to change direction. The person is not being trapped, but their movement through the room is affected by how strongly they interact with the crowd. In a rough way, particles that interact strongly with the Higgs field behave as if they have more mass. Particles that interact weakly have less. Particles that do not interact with it in the relevant way remain massless. The analogy is imperfect, because a quantum field is not a crowd of people, and particles are not celebrities trying to reach the snack table. But it gives a useful first impression. The amount of interaction matters. This helps explain why different fundamental particles have different masses. An electron has a small mass because it interacts with the Higgs field weakly. Some heavier particles interact more strongly. Photons, the particles of light, do not gain mass from the Higgs field in this way, which is why light travels at its natural speed through empty space. If photons had mass, the behavior of light and electromagnetism would be very different, and the universe would not be the one we know. The Higgs field is not giving everything mass equally. It is selective. The field is everywhere, but particles respond to it according to their own connections with it. This background presence of the Higgs field is one reason the vacuum is so different from ordinary nothing. If empty space were simply the absence of all fields and all structure, there would be no Higgs background for particles to interact with. But in our universe, the vacuum includes the settled state of the Higgs field. That settled state is woven into the properties of matter. In a very real sense, what we call empty space helps determine the masses of many of the particles from which atoms are built. The vacuum is not just the place matter occupies, it helps matter have some of its basic properties. This may sound as if all mass comes from the Higgs field, but that would be too simple. The visible matter around us is made mostly of atoms, and most of the mass of atoms comes from the protons and neutrons in their nuclei. Protons and neutrons are made of quarks, and quarks do get some of their mass from the Higgs field. But most of the mass of a proton or neutron does not come directly from the masses of the quarks inside it. It comes from the energy of the strong force that binds the quarks together, from the intense activity of the fields inside those particles. Energy and mass are deeply connected, so the internal binding energy contributes most of the mass of ordinary matter. In other words, the Higgs field is essential, but it is not the only source of mass in the everyday world. This distinction matters because it keeps the story accurate. The Higgs field gives mass to many fundamental particles, including quarks and electrons, and without it atoms as we know them would not exist. But the weight of your chair, your hand, the earth, and a sleepy cat on a blanket is mostly due to the energy contained in the protons and neutrons inside atoms. The Higgs field sets the stage by giving fundamental particles their individual masses, while the strong nuclear force contributes much of the mass of the composite matter we actually touch. Reality likes to divide the labour. Even mass has a committee. The Higgs field became especially famous because of the Higgs boson. A boson is a particle associated with a field, a detectable excitation of that field. Just as a photon is an excitation of the electromagnetic field, the Higgs boson is an excitation of the Higgs field. If the field is like an invisible presence spread through space, the Higgs boson is like a small ripple in that presence. For decades, physicists believed the Higgs field should exist because it made the theory of particles and forces work in a coherent way. But to confirm the idea, they needed to detect the particle associated with the field. That required enormous energies because the Higgs boson is heavy and unstable. It appears briefly in high-energy collisions and quickly decays into other particles. It does not sit around politely waiting to be placed in a jar. The discovery of the Higgs boson at the Large Hadron Collider was a major milestone because it provided strong evidence that the Higgs field is real. Scientists did not see the Higgs boson directly in the simple sense of taking a photograph of it. Instead, they collided particles at tremendous energies and studied the patterns of decay products that emerged. They looked for an excess of events matching what the Higgs boson should produce. Over time, the evidence became strong enough to announce the discovery. It was a triumph of theory, engineering, statistics, patience, and probably a great deal of coffee. But the Higgs boson should not distract us from the deeper idea. The boson is the ripple, the field is the sea. The discovery of the ripple confirmed the presence of the field, but the field itself is what matters for the mass of particles. Even when no Higgs bosons are present, the Higgs field fills space in its vacuum state. That is why the vacuum is important. The mass-giving role of the Higgs field does not require space to be full of actual Higgs bosons. It requires the background field value that exists in empty space. This is another place where language can lead us astray. Saying the Higgs field fills space might make it sound like space is packed with a material that could be scooped or stirred. It is better to think of it as a field condition that exists everywhere. We do not feel it as a wind. We do not see it as a glow. It does not create a preferred direction in space. It is uniform, so it does not make particles drift one way or another. Because it is the same everywhere, we normally do not notice it directly. It is like a rule built into the background of the world. Only when we study particle masses and high-energy collisions does its presence become clear. This uniform background is also important because it does not break the ordinary appearance of space. If the Higgs field pointed in some direction, or varied from place to place in an obvious way, physics would look different depending on where you were or which way you faced. Instead, the Higgs field's vacuum state is the same in all directions, so it can give particles mass without making space visibly lopsided. The vacuum has structure, but it is a very subtle kind of structure. It can be present everywhere while still preserving the smoothness of ordinary empty space. The Higgs field is connected with a process called symmetry breaking. The phrase sounds dramatic, but the basic idea can be explained without equations. A system can have rules that are symmetrical, meaning the underlying laws treat possibilities evenly. But the actual state the system settles into may choose one of those possibilities, making the world look less symmetrical than the laws themselves. A simple example is a pencil balanced perfectly on its tip. In principle, it could fall in any direction. The situation is symmetrical, but once it falls, it picks one direction. The rules did not prefer that direction in advance, but the final state does. The Higgs field works in a more complex and quantum way, but the idea is similar. The laws have a symmetry, and the vacuum state of the Higgs field settles into a condition that changes how particles behave. This settling of the Higgs field in the vacuum is what allows certain particles to acquire mass, while the broader theory remains consistent. Before this idea, the mathematical description of some particle interactions faced a serious problem. Adding mass directly in the simplest way would break the structure of the theory. The Higgs mechanism solved the problem by letting mass arise through interaction with the background field instead. It is not a patch stuck on at random. It is an elegant way for the theory to keep its deeper order while describing the real particles we observe. There is a remarkable consequence here. The properties of particles are not only private possessions of the particles themselves, they depend on the vacuum state of the fields around them. If the Higgs field had a different background value, particles would have different masses. If it had settled differently in the early universe, Matter might not form atoms in the same way. Chemistry could fail. Stars might not burn as they do. Planets might not form. The universe could be a place with different rules for structure and complexity. The ordinary existence of matter depends on the vacuum having the properties it has. This connects the Higgs field to the early universe. In the hot, dense conditions shortly after the Big Bang, the Higgs field may not have been settled into the same vacuum state it has today. As the universe expanded and cooled, the field took on its present background value. This transition helped shape the particle masses we now observe. The vacuum was not always experienced by the universe in the same way. Its state evolved as the cosmos cooled. That means the story of mass is also a story of cosmic history. The vacuum we live in is not simply a static emptiness. It is the outcome of how fields settled as the universe changed. This idea can feel almost unsettling. The mass of your hand, the behaviour of atoms, the existence of chemistry, the shining of stars, all depend partly on a field whose background state fills the vacuum, yet there is no sensation of moving through it. You can wave your hand through the air and feel air resistance, but you cannot feel the Higgs field as a breeze. It is too deeply woven into the rules of particle behaviour. It is not something added to the universe in a noticeable everyday layer. It is part of the reason the everyday layer has its form. The vacuum then becomes less like an empty theatre and more like a theatre whose floor quietly determines the weight of every actor's shoes. The actors do not notice the floor as a separate object because they have never known a stage without it. Their movements, their balance, and their resistance to being pushed are all shaped by it. In the universe, particles do not move through a neutral nothing. They exist in the presence of fields, including the Higgs field, and their properties are partly determined by that presence. The vacuum is not scenery, it is part of the script. Of course, many questions remain. The Higgs field gives us a mechanism for particle masses, but it does not fully explain why each particle interacts with the field by exactly the amount it does. Why does an electron have its particular mass and not another? Why are some particles much heavier than others? Why is the Higgs field's background value what it is? These questions point beyond the current standard model and into deeper mysteries. The discovery of the Higgs boson confirmed a major piece of the picture, but it did not close the book. It opened new pages. The Higgs field also brings us close to questions about the stability of the vacuum itself. If the vacuum is a state of fields, then we can ask whether it is the absolute lowest possible state or merely a long-lived state that appears stable for now. Some calculations suggest that the Higgs field may place our vacuum in a condition that is stable enough to last far longer than any timescale relevant to ordinary life, but perhaps not the deepest possible state in every theoretical sense. This leads to ideas such as false vacuum decay, which sound alarming and are best approached later with calm voices and no sudden movements. For the moment, it is enough to know that the Higgs field does not merely explain mass, it also touches questions about what kind of vacuum our universe occupies. That is the larger pattern of this journey. Every time we try to make the vacuum simple, another layer appears. First, it was not just airless space. Then it was a state of quantum fields. Then it had fluctuations. Then it produced tiny forces between close surfaces. Now it helps give fundamental particles mass. Empty space is beginning to look less like the absence of physics and more like one of physics' central characters. It is quiet, yes, but it is not idle, and this quiet role of the Higgs field is especially important because it connects the vacuum to the matter of daily life. The Casimir effect is real but tiny, noticeable only under special conditions. Vacuum fluctuations are subtle, appearing in precision measurements, but mass is everywhere in our experience. The effort required to lift a cup, the momentum of a moving train, the stability of atoms, the weight of a sleeping body, all of these belong to a world where particles have mass and energy is organized into matter. The Higgs field is not the whole story of mass, but it is one of the reasons the fundamental ingredients of matter are not all weightless flashes racing at light speed. It helps make the universe slow enough, stable enough, and structured enough for complexity. So when you imagine the vacuum now, it may no longer feel like a cleaned out room. It is closer to an invisible background condition that shapes what can exist inside it. The Higgs field lies quietly there, not glowing, not flowing, not dragging, but present. Particles that couple to it carry mass because of that relationship. The vacuum becomes a kind of hidden foundation for the familiar resistance of matter. It helps explain why the world has weight, why objects do not all behave like light, why atoms can form and chemistry can unfold. From here, the question widens again. If the vacuum contains fields, fluctuations, and the Higgs background, then what about its energy on the scale of the whole universe? Does empty space weigh something in a gravitational sense? Can the vacuum itself help drive the expansion of the cosmos? When astronomers look at distant galaxies, they find that the universe is not only expanding, but that this expansion is accelerating. One possible way to describe that acceleration is through energy associated with empty space itself. The vacuum that gave us mass now begins to reach outward into cosmology, where the emptiest regions between galaxies may help decide the future of everything. Fact anchor. Before the narration, Nisa describes dark energy as the unknown driver of the universe's accelerating expansion, and recent DESI results have reported hints that dark energy may evolve with time, though this remains an active question rather than a settled conclusion. The Higgs field brought the vacuum close to home, into the mass of particles, the structure of atoms, and the quiet resistance matter has when you try to move it. But the vacuum does not stop at the scale of particles. It also stretches outward into the largest question we can ask about space itself. When we look between galaxies, across distances so wide that even light takes billions of years to cross them, empty space begins to matter in a new way. Not as a tiny force between plates, not as a background that helps particles gain mass, but as something that may influence the expansion of the entire universe. The emptiest regions of the cosmos may not merely sit there while galaxies drift apart. They may be part of the reason the drifting speeds up. That idea is so strange that it is worth approaching slowly. For most of human history, the universe was imagined as a set of things. Stars, planets, moons, clouds, comets, and the dark spaces between them. Matter was the actor. Space was the background. If anything had weight, pull, influence, or importance, it was probably matter. A stone had mass. A planet had gravity. A star had light and heat. Empty space seemed to have no opinion. It was the gap between meaningful objects, the quiet dark between the glowing points. But modern cosmology has taught us that the gap itself may have a role in the fate of everything. The story begins with expansion. In the early 20th century, astronomers discovered that distant galaxies are moving away from us, and more importantly, that the farther away they are, the faster they seem to recede. This does not mean Earth is sitting at the special centre of a cosmic explosion, watching everything flee in embarrassment. It means space itself is expanding. The distances between large clusters of galaxies grow over time, not because galaxies are flying through space like sparks through a room, but because the space between them is stretching. On smaller scales, gravity holds galaxies, solar systems, planets, and people together. Your chair is not expanding away from the floor, which is reassuring. But across the largest cosmic distances, the universe grows. At first, it seemed natural to imagine that this expansion should slow down. Matter attracts matter through gravity. Galaxies pull on one another. Even if the universe began expanding long ago, gravity should act like a brake, gradually reducing the rate of expansion. The big question was how much it would slow. Would the universe expand forever, more and more gently? Would gravity eventually halt the expansion and pull everything back together? Would it balance on the edge? These were grand questions, but they all shared one assumption. The expansion should be slowing. Then observations of distant, exploding stars changed the mood in the room. These stars, used as cosmic distance markers, allowed astronomers to measure how the expansion rate had changed over time. The result was unexpected. The universe was not merely expanding, its expansion was accelerating. The distances between faraway galaxies were increasing faster and faster. Gravity by itself should have been pulling the other way. Something else seemed to be acting on cosmic scales. Something that behaves not like ordinary matter pulling inward, but like a tendency of space itself to drive expansion outward. Scientists gave this unknown cause the name dark energy. The name is honest in a way. Dark energy is not called dark because it is sinister, or because it wears a cloak and waits near the edge of the telescope. It is called dark because we do not see it directly as light, and because its nature remains unknown. It is not dark matter, which is a different mystery involving unseen mass that helps hold galaxies and clusters together. Dark matter pulls through gravity like matter does. Dark energy seems to be associated with the accelerated expansion of space. The names sound like they belong in the same storage cupboard, but they are not the same thing. The universe, it turns out, has several kinds of darkness, because apparently one was not enough. One of the simplest explanations for dark energy is the cosmological constant. The phrase comes from Einstein's work on general relativity. Einstein introduced a constant into his equations when he was trying to describe a static universe, one that did not expand or contract. At the time, many scientists believed the universe was eternal and unchanging on the larger scales. Einstein's original equations suggested a dynamic universe, which was uncomfortable for that older view. So he added a term that could counterbalance gravity and hold the universe still. Later, after evidence showed that the universe is expanding, the constant seemed unnecessary, even mistaken. But physics has a habit of leaving old ideas in the attic until one day someone realizes they may be useful after all. When cosmic acceleration was discovered, the cosmological constant returned in a new role. Instead of holding the universe static, it could represent a steady energy of empty space itself. If the vacuum has a constant energy density, then as space expands, new space also contains that same kind of energy. Ordinary matter becomes more diluted as the universe expands, because the same particles are spread through a larger volume. Radiation thins out even more strongly because its light is stretched as space expands. But a cosmological constant does not thin in that way. Its energy density remains the same in each region of space. As the universe grows, there is more space, and the total amount of this vacuum energy grows with it. This sounds suspicious at first, as if energy is being created from nowhere. But in general relativity, energy in an expanding universe is not always conserved in the simple, everyday way we expect from a closed box. The universe is not a box sitting inside a larger room. Space itself is dynamic. The rules of cosmic accounting are more subtle. This does not mean anything goes. It means that our familiar ideas about energy, learned from engines, falling objects, and household bills, do not transfer perfectly to the whole expanding cosmos. The universe does not send us a monthly statement explaining where every unit went, which is probably for the best. The key feature of the cosmological constant is pressure. In ordinary life, pressure usually pushes outward, because particles are moving and colliding. Air pressure inside a balloon pushes the rubber surface outward. Gas pressure in a tire keeps it inflated. But in cosmology, pressure affects gravity. Ordinary positive pressure can contribute to gravitational attraction. The vacuum energy associated with a cosmological constant behaves differently. It has a kind of negative pressure. This is not negative pressure like a suction cup stuck to a window in the everyday sense. It is a property of the vacuum energy in the equations of general relativity. The effect is gravitationally repulsive on cosmic scales, causing the expansion of space to accelerate. That is where the phrase "the weight of empty space" becomes both useful and strange. Empty space does not weigh something in the same way a bag of apples weighs something. You cannot place a cubic meter of vacuum on a bathroom scale and expect it to complain about holiday meals. But in general relativity, Energy and pressure influence the curvature and expansion of space-time. If the vacuum has energy, then it has gravitational effects. The vacuum can help shape the large-scale motion of the universe. Its weight is not a downward pull in a room. It is a contribution to cosmic dynamics. This links back to everything we've been discussing. Quantum field theory tells us that the vacuum is not simply nothing. It is the lowest energy state of fields. It has fluctuations. It has structure. The Higgs field has a background value. So it is natural to ask whether the vacuum has energy, and whether that energy could be the dark energy of cosmology. The cosmological constant is, in one sense, the idea that empty space has a steady energy that drives acceleration. It seems like a clean connection between the smallest and largest scales. The quantum vacuum has energy. The universe accelerates as if space has energy. Perhaps these are the same story. And then the trouble begins. The problem is that when physicists try to connect vacuum energy from quantum field theory with the observed dark energy of cosmology, the numbers do not match in any simple way. The theoretical expectations, depending on how the calculation is framed, can be enormously larger than what the universe appears to allow. This mismatch is one of the deepest puzzles in modern physics. It is sometimes called the cosmological constant problem, though that name is far too tidy for the size of the headache it has caused. It is as if you ordered a teaspoon of sugar and the delivery truck arrived carrying a mountain, then handed you a receipt saying everything was perfectly normal. This puzzle does not mean the theories are useless. Quantum field theory works incredibly well for particle physics. General relativity works incredibly well for gravity and cosmology. The problem appears when we try to make them speak about the vacuum energy of the entire universe in one fully consistent way. The small world and the large world each have excellent rules, but the place where they meet is still not fully understood. Dark energy sits right in that meeting place. It asks what empty space is, how energy gravitates, how quantum fields behave on cosmic scales, and whether our current theories are missing something important. There are several possible ways forward. The simplest is that dark energy really is a cosmological constant, a steady property of empty space that does not change over time. This idea fits much of the evidence and remains a central part of the standard model of cosmology. It is simple, elegant, and strangely stubborn. It says that the vacuum has a constant energy density, and that this energy now dominates the expansion of the universe because matter has become diluted over cosmic time. Billions of years ago, matter was packed more densely, and its gravity had more influence. As the universe expanded, matter thinned out, while vacuum energy remained steady. Eventually, dark energy became the dominant factor, and expansion began to accelerate. Another possibility is that dark energy is not constant. It may be caused by a field that changes slowly over time, sometimes called an evolving dark energy field. In that case, the acceleration of the universe might change in the future. It could strengthen, weaken, or behave in ways that current observations have not yet pinned down. Recent large surveys have reported hints that dark energy may not be perfectly constant, but this remains uncertain. Cosmologists are cautious because extraordinary claims require careful agreement among many kinds of data. Supernovae, galaxy clustering, the cosmic microwave background and other measurements must all be compared. The universe is generous with clues, but it rarely labels them clearly. A third possibility is that our understanding of gravity itself needs adjustment on the larger scales. General relativity has passed many tests, from the motion of planets to gravitational waves, but dark energy raises the question of whether gravity behaves differently across the vastest cosmic distances. Modified gravity theories try to explain acceleration without adding a separate dark energy substance or field. Instead, they change the rules of gravity in subtle ways. So far, no alternative has replaced the standard picture, but the search continues because the mystery is large enough to justify careful imagination. There is also the possibility that the answer involves new physics we do not yet know how to frame. The vacuum may have deeper structure. Quantum gravity may change how vacuum energy should be understood. The universe may contain fields or symmetries not yet discovered. Or the small observed value of dark energy may be tied to selection effects, meaning that only universes with certain vacuum properties allow galaxies, stars, planets, and observers to exist. This idea is controversial and difficult, but it appears in discussions of the broader landscape of possible vacuum states. It is the kind of idea that makes physicists stare thoughtfully into coffee. For the purposes of our calm journey, the central point is this. Dark energy suggests that empty space is not gravitationally irrelevant. The vacuum may have a large-scale effect on the expansion of the universe. It may not be made of particles in the familiar sense. It may not clump around galaxies like matter. It appears to be spread smoothly through space, or at least much more smoothly than matter. It does not shine. It does not form planets. It does not gather into dark energy clouds with little dark energy weather reports. Yet it seems to dominate the current behavior of the cosmos. This is a striking reversal of intuition. Matter feels important because it forms objects. Stars shine, planets turn, rocks sit stubbornly. People make soup and ask complicated questions before sleep. Empty space feels secondary. But on the larger scale, matter may be the smaller part of the energy budget, while dark energy may be the dominant component. The universe is not ruled only by the bright things we see. It may be shaped most strongly by the emptiness between them. The future depends on what dark energy is. If it is truly a cosmological constant, the universe may continue expanding forever at an accelerating pace. Distant galaxies not gravitationally bound to us will move beyond our observable horizon. Over immense spans of time, the night sky available to future observers may become emptier, with fewer distant galaxies visible. Local galaxies bound together by gravity may remain, but the wider cosmos would fade from view. This possible future is sometimes called a cold or lonely fate, though from the point of view of a sleepy astronomer, it is less an event and more an extremely long dimming of the cosmic room. If dark energy changes with time, the future could be different. If it weakens, cosmic acceleration might slow. If it strengthens, expansion could become more extreme. Some speculative possibilities involve a universe that eventually tears apart bound structures, but those require particular kinds of dark energy behavior and are not the standard expectation. Other possibilities involve a slowing expansion or even a future contraction, though these remain uncertain. The fate of the universe is tied to the nature of the vacuum, and that nature is still being measured. There is something humbling about the way this mystery sits between observation and theory. Dark energy was not invented because physicists wanted the vacuum to be dramatic. It was inferred because distant objects did not behave as expected. The expansion history of the universe demanded an explanation. The cosmological constant offered one. Evolving fields and modified gravity offer others. New surveys continue to refine the picture. The subject is alive, not settled into a final bedtime answer. This is not a weakness. It is how science works when it reaches the frontier. The map is clear in some regions and misty at the edges. The vacuum, then, has become a meeting place for questions. In particle physics, it is the ground state of fields. In quantum theory, it fluctuates. In the Higgs mechanism, it gives many particles mass. In cosmology, it may carry energy that accelerates the universe. These ideas are connected, but not yet unified into one complete understanding. Empty space is not just a place where things are absent. It is a problem, a clue, a measured influence, and perhaps a doorway into deeper physics. As you rest with that idea, it may help to picture the dark spaces between galaxies not as dead gaps, but as the arena where the expansion of the universe reveals its deepest habit. The galaxies are like bright markers floating in a stretching fabric. The fabric is not a material sheet, but the image helps. The markers show us how distances change. The pattern of their motion tells us that something about space itself is affecting the cosmic expansion. Whether that something is a true cosmological constant, a changing field, or a sign that gravity has more to teach us, the vacuum is no longer just silence between the notes. It is part of the music's timing, and yet this leads to one final uneasy thought. If the vacuum is a physical state of fields, and if fields can have different possible states, then how certain are we that our vacuum is the final and safest one? The Higgs field settled into the background value that gives particles mass. Dark energy may reflect a property of empty space, but physical systems can sometimes rest in states that are stable for a very long time without being the absolute lowest state possible. A ball can sit in a shallow valley while a deeper valley exists beyond a hill. It will stay there unless something gives it enough help to cross the barrier. That kind of idea, applied to the fields of the universe, brings us toward the strange notion of a false vacuum, cosmic stability, and the unsettling but fascinating question of whether the nothing beneath everything could ever change its mind. After the long quiet path through empty space, quantum fields, restless vacuum fluctuations, delicate forces, the Higgs field, and the expansion of the universe, we arrive at a question that sounds at first like the kind of thing one might prefer not to ask just before sleep. If the vacuum is not simple nothing, if it is a physical state of fields, could that state ever change? Could the emptiness beneath everything be stable for now, but not stable forever? Could the vacuum of our universe be less like the lowest floor of reality and more like a resting place on the way to a lower one? This is the idea behind the false vacuum, and although it has a dramatic name, we can approach it calmly. It is not a prediction that something is about to happen. It is a way physicists think about the possible states of fields, and about whether the vacuum we live in is the deepest possible state, or simply a very long-lived one. A helpful first image is a ball resting in a valley. If the ball sits at the very bottom of the deepest valley anywhere nearby, then it is in the most stable position it can have. If you nudge it slightly, it rolls back down. It has nowhere lower to go, but imagine another situation. The ball sits in a small valley, a comfortable dip in the landscape with hills around it. It seems stable because small nudges do not move it far. It rolls back to the same spot. Yet beyond one of the hills, there is a much deeper valley. If the ball could somehow get over the hill, it would roll down into that deeper place and never return. The first valley was stable in daily practice, but not absolutely stable. It was a local resting place, not the deepest possible resting place. In physics, fields can have something like landscapes of possible states. These are not landscapes made of soil and grass, and there are no little field hikers carrying sandwiches through them. The image simply helps us imagine that a field may have different possible conditions, each with a different energy. The vacuum is the state the field settles into when it is not excited with particles. If that state is the lowest possible one, it is called a true vacuum. If it is a resting place that is lower than nearby states, but not the lowest state overall, it is called a false vacuum. False does not mean fake in the ordinary sense. It does not mean our universe is imaginary or unreliable. It means the vacuum may be stable against small disturbances while still not being the absolute lowest energy state available to the fields. That distinction matters because the world can remain in a false vacuum for an incredibly long time. A local valley can hold the ball for ages if the surrounding hill is high enough. In classical thinking, the ball would need enough energy to climb over the hill. If it never gets that energy, it never leaves. But quantum physics allows a more unusual possibility called tunneling. A system can move from one allowed state to another, even if, in a classical picture, it would not have enough energy to cross the barrier between them. It is not a little object digging a tunnel with a tiny shovel. It is a quantum process where the system has a small probability of appearing on the other side of a barrier. For a field in a false vacuum, tunneling could mean a transition to a lower energy vacuum state. This is where the idea becomes cosmic. If a field that fills space were to transition from a false vacuum to a true vacuum, the change would not necessarily happen everywhere at once. It could begin in a tiny region, a small bubble of the new vacuum. Inside that bubble, the field would be in the lower energy state. The boundary of the bubble would separate the new vacuum from the old one. If the new state were energetically favoured, the bubble could expand outward, converting more and more space into the new vacuum. In many theoretical descriptions, such a bubble would expand extremely quickly, close to the speed at which light travels. Anything in its path would be changed as the fundamental field state changed. That sounds like a dramatic science fiction ending, but it is important to keep the scale of the possibility in mind. The false vacuum idea is not something observed happening around us. It is not a known threat waiting nearby. It is a theoretical possibility that arises in discussions of quantum fields and cosmology. Based on what we know, our vacuum appears extraordinarily stable. Even if it were technically metastable, meaning stable for a very long time but not absolutely stable, its expected lifetime could be far, far longer than the present age of the universe. This is not like a crack in the ceiling that should be inspected before morning. It is more like a mathematical question about the deeper structure of the fields, asked across timescales so large they make ordinary fear lose its grip. The Higgs field is central to many modern discussions of vacuum stability. The same field that helps give mass to many fundamental particles also has a vacuum state. The properties of the Higgs field are connected to whether the current vacuum of the universe is absolutely stable or only metastable. Measurements of the Higgs boson and other particles suggest that our universe may sit near a boundary between different possibilities. Depending on the exact values and on physics not yet discovered, the vacuum could be stable, or it could be metastable but with a lifetime so enormous that for every practical purpose it is safe. The answer is not fully settled because it depends on precise measurements and on whether the known particles and fields are the whole story. New physics could change the conclusion. This is a useful reminder that scientific uncertainty is not the same as danger. When physicists say the vacuum might be metastable, they are not announcing that the universe is fragile in an everyday sense. They are describing what current theories suggest when stretched to very high energies and enormous timescales. The vacuum has already lasted through the violent early universe, through the formation of galaxies, through exploding stars, through the birth of planets, and through billions of years of cosmic history. It has endured conditions far more extreme than anything found in ordinary life. If the vacuum were easily disturbed, we would not be here discussing it in a calm room with the lights low. Some people hear about particle accelerators and wonder whether high-energy collisions could trigger vacuum decay. This worry has been examined many times, and the reassuring answer is that nature has already performed much more energetic experiments than we can create on Earth. Cosmic rays, which are high-energy particles from space, strike the atmosphere, the moon, stars, and other bodies with energies that can exceed human-made collisions. These natural collisions have been happening for billions of years. If such events could easily trigger a dangerous vacuum transition, the universe would have revealed that long before any laboratory was built. Particle accelerators let us study nature under controlled conditions, but they do not create a kind of risk that the cosmos has not already tested on a far grander scale. False vacuum ideas also appear in theories of the early universe. In some models, the universe may have gone through periods when fields were trapped in high-energy vacuum states before transitioning to lower ones. These transitions could have released energy and shaped the evolution of the cosmos. One famous idea, cosmic inflation, suggests that the very early universe expanded extremely rapidly for a brief period, possibly driven by a vacuum-like energy associated with a field. Different versions of inflation use different mechanisms, and not all rely on false vacuum decay in the same way. But the general theme is that vacuum states can influence cosmic history. The vacuum is not only a quiet condition after the universe has formed, it may have played a role in forming the large-scale structure we see today. The idea of bubbles of vacuum also appears in more speculative discussions of multiple possible universes. If different regions of a larger reality could settle into different vacuum states, then each region might have different particle masses, forces, or cosmic properties. This is sometimes discussed in connection with a landscape of possible vacua. The phrase sounds grand, and it is, but it remains speculative. We should handle it carefully. It is not something we have directly observed. It is a way some theories try to understand why our universe has the particular vacuum properties it has. Still, it shows how far the question of empty space can reach. What began as a question about airless space has grown into a question about the possible forms a universe can take. A false vacuum would not be false because everything inside it is unreal. If our vacuum were metastable, the atoms in your body would still be real. The chair, the stars, the planets, the history of the universe, all of it would be real within this vacuum state. The laws of physics we measure would be the laws that operate here. A change to a lower vacuum would change the underlying field conditions, and with them the behaviour of particles and forces. That is why such a transition would be so significant. It would not be like weather changing, or a star exploding, or a galaxy moving. It would be a change in the background rules that allow ordinary matter to exist as it does. Because this sounds so large, it is worth bringing the idea back to everyday scale. Many ordinary systems are stable in one sense, but not in another. A book on a table is stable if you tap it gently. It stays there. But if the table is tilted enough, the book slides. A pencil balanced on its flat end is stable, but balanced on its tip it is unstable. A snowpack on a mountain can remain still for a long time, then shift if conditions change. These comparisons are not perfect, because fields and quantum tunneling are not books or pencils or snow. But they help show that stability is not a single simple idea. Something can be stable against small changes, unstable against large changes, or stable for so long that the difference between perfect and practical stability barely matters. Our vacuum appears stable in the practical sense. The universe is old and the vacuum has persisted. The fields around us are not flickering into new laws. Matter behaves consistently. Atoms do not change their basic properties from one morning to the next. Light, gravity, chemistry, and nuclear physics operate with remarkable reliability. The fact that we can do science at all depends on this stability. If the vacuum were constantly wandering between states, the universe would not support the kind of ordered complexity we observe. The calm continuity of nature is itself evidence that the vacuum state is deeply robust. Still, thinking about false vacuum decay teaches a valuable lesson. It shows that the vacuum is not merely the absence of things, it is a state, and states can be compared, studied, and sometimes changed. A cup of water can be liquid, ice or vapour depending on conditions. A magnet can have its internal alignment arranged in different ways. A field can also have different possible vacuum states depending on its underlying structure. The vacuum is not a word for no physics. It is a physical condition within physics. That is why the question of its stability makes sense. This connects all the earlier ideas into one larger picture. Empty space began as a simple absence of air. Then we saw that even outer space is not perfectly empty. Then quantum fields appeared as the invisible foundation of particles. The vacuum became the quiet state of those fields, but not a perfectly still one. Vacuum fluctuations influenced atoms and forces. Virtual particles appeared as useful internal bookkeeping in quantum interactions. The Casimir effect showed that boundaries can shape the vacuum and create a tiny measurable force. The Higgs field showed that the vacuum helps give many particles mass. Dark energy suggested that the vacuum may influence the expansion of the universe. Now, false vacuum stability asks whether this entire background state is the final one, or merely one that has lasted long enough for galaxies, stars, planets, biology, and late-night questions to arise. There is a quiet seriousness to that progression. Each step makes the vacuum less like nothing, and more like a central part of reality. It is not a material in the ordinary sense, but it has properties. It is not an object, but it can affect objects. It is not matter, but it helps determine how matter behaves. It is not empty in the deepest sense, but it can still be called empty in the practical sense. The vacuum is one of those ideas that becomes richer as we remove assumptions from it. We remove air and discover pressure. We remove matter and discover fields. We remove particles and discover fluctuations. We remove certainty and discover possible vacuum states. It is also worth noticing that false vacuum decay, if it exists as a possibility, would not be something anyone could see coming in the ordinary way. A bubble of lower vacuum would expand so rapidly that there would be no warning signal arriving ahead of it. This sounds unsettling, but it also means it is not a useful object of daily worry. It belongs to the category of cosmic possibilities that are interesting to understand but not practical to fear. Human life is full of real concerns that deserve our attention, kindness, and planning. Vacuum decay is not one of the things that needs to be added to tomorrow's list. The universe has carried this vacuum for billions of years, and the best scientific understanding gives no reason to treat it as an imminent danger. In fact, the idea can be strangely calming when held correctly. It places us inside a universe whose stability is not trivial, but remarkable. The fields have settled into a state that allows atoms, light, stars, planets, and minds. The vacuum is not a blank nothing beneath us. It is a structured condition that has supported the entire history of everything we know. If it is absolutely stable, then it is the deep floor of our physical reality. If it is metastable, then it is still stable beyond imagination for all ordinary purposes. Either way, the universe we inhabit is not flimsy. It has endured. The future of nothing, then, is not really about nothing. It is about what the vacuum may become, or continue to be, across the longest stretches of time. If dark energy remains constant, distant galaxies will drift beyond view, and the observable universe will slowly empty. If stars burn out and matter spreads thin, the cosmos may become colder and quieter. If the vacuum is absolutely stable, that long fading may continue according to the known rules. If the vacuum is metastable, an unimaginably rare transition could one day change the rules themselves. These are futures so vast that ordinary time loses its familiar meaning. They are not tomorrow, not next year, not the next age of civilization. They are the far horizon of theoretical cosmology. And here, after all this, the vacuum has become almost the opposite of what the word first promised. It began as emptiness, a cleaned-out space, an absence. But now it carries fields, fluctuations, forces, mass, cosmic acceleration, and possible stability questions. It is quiet, but not simple. It is empty, but not featureless. It is the background of physics, and also one of physics' hardest problems. The vacuum is what remains when we remove ordinary things, and what remains is not nothing. It is the deep arrangement that allows ordinary things to exist. So as the mind begins to soften, there is no need to picture the vacuum as alarming. Picture it instead as the most silent part of the universe, but a silence with rules. The space between stars, the space between atoms, the space in a carefully pumped chamber, all of it belongs to a world where fields have settled into a steady state. That state has been stable enough for time to build galaxies, for stars to make elements, for planets to cool, for life to notice the night sky, and for someone somewhere to wonder what emptiness really means. The vacuum is not a hole in reality, it is reality at its quietest, and perhaps that is the gentlest place to leave the thought, not with fear of strange futures, but with appreciation for the strange stability of the present. The room around you may seem ordinary, the air may be still, the dark corners may look empty. Yet beneath that ordinary quiet is a layered physical world, full of fields in their settled states, particles resting or moving according to rules, light crossing space, gravity shaping distances, and the vacuum holding its deep calm. We began by asking what the vacuum is really made of, and the answer turned out not to be a list of ingredients, but a change in how we understand emptiness. The vacuum is not made of dust, air, or hidden little objects. It is made, if we can use that word gently, of the ground states of the fields that fill the universe, of the conditions that remain when matter is gone, of the quiet structure beneath everything. So wherever you are listening from, whatever the hour says on the clock near you, let the idea settle without needing to solve it. Empty space is not empty in the way we first imagined. It is calm, stable, and deeply physical. It gives the universe a background on which matter can appear, forces can act, light can travel, and time can unfold. The nothing between things is not a useless gap. It is part of the reason there are things at all, and as the day loosens its grip and the mind drifts toward rest, the vacuum can return to what it has always been around you, unseen, unfelt, steady, and quietly holding the stage while everything else takes its turn beneath the stars.